Hi everyone, welcome to this video that's going to tell you everything you need to know for your A-level Physics Paper 1. This is specifically for AQA students, but 90% of the content is for all exam boards, so you should find it useful anyway. So we're going to start off with particle physics. So all matter, to start off with, can be split off into two subcategories, either leptons or hadrons. Now, hadrons are not fundamental particles, we'll come on to them later, but leptons are, and I guarantee you'll know a couple of them already. So leptons, the main lepton you've come across before is the electron. So the electron has a negative charge. We signify that by the little negative symbol here. In the lepton family, we also have muons and tauons. Now, muons, we come across where they are types of cosmic rays coming down to Earth. They're about 200 times heavier than the electron, still have a negative charge. Tauons are even heavier, but we don't come across those at A level, but it's useful to know they're there. Also in the lepton family, we have the neutrino, which has this symbol nu. The symbol for it's kind of like a curly V, and they come in three flavors. Yes, that's right, flavors. They come in electron, muon, or tauon flavors, and they are neutral, as the name suggests. So they are the only uncharged lepton, and they are incredibly small. They are virtually massless, and that means they are very, very difficult to detect. It takes a lot of effort to detect one. They very rarely interact with matter. So how do we know they exist? Well, they are hypothesized in beta decay. So beta decay had a big problem, which was that when the neutron changed into a proton and released a beta particle, if you add together the energy of the proton and the beta particle, you end up with less energy than was initially locked up inside the neutron. So the hypothesized particle was thought up by Paul Dirac to carry away that extra energy. And they knew it must be neutral, and they knew it must be very, very, very small mass, because otherwise it would be found it already. And they hypothesized it was the neutrino. Now, in this instance, it's an anti-neutrino, which is an antiparticle. We'll come on how we know that a little bit later. But it's a good excuse to look at antimatter and antiparticles early on. So all these leptons have antiparticles. So antineutrinos, as we've discussed, we have an anti-electron, which is called a positron. We have an anti-muon and anti-tauon. And for their symbols, you might have noticed the negative sign changes to a positive sign. So that gives us a big clue into what antiparticles are. Which is that they have the opposite charge to their regular particle counterparts. So a positron is exactly the same as an electron, apart from it now has a positive charge. Everything else is the same, so it'll have the same mass, the same, like every other characteristic about the particle will be the same apart from the charge, which makes it an antiparticle. Let's look at where we might find this positron being emitted. It actually gets emitted in something called beta plus decay. So in beta plus decay, instead of a neutron changing to a proton, we have a proton changing to a neutron, and then a positron or positive electron is emitted along with a regular neutrino. Now, something very interesting happens when you have a particle and its antiparticle meet. So, for example, it could be an electron and a positron. Now, when they meet, when they come together, they cease to exist. It's absolutely mad to think about, but two particles can just basically disappear. That process is called annihilation. And it doesn't just disappear into nothing, but it disappears into energy. So in annihilation, the matter inside the particles is converted to pure energy in the form of waves. We could say the mass is converted to energy, and that is given by E equals mc squared, which we'll do a calculation with later. But E is energy and m is mass. So let's have a look at a specific example then. So let's say we have an electron that meets a positron. They meet with a significant amount of energy head-on, and these two gamma rays are emitted up and down to conserve momentum. So we can calculate the energy that these photons are going to have due to what's called the rest energy of the electron and of the positron. Now, the rest energy, to define a key term early on, as the name kind of suggests, rest means no velocity. So rest energy is the energy locked up in a particle's mass if it was all converted to energy by E equals mc squared. So these particles might have kinetic energy, but the energy we're looking at here is the energy if you were to convert all of their mass straight into energy. So c in this equation is the speed of light, so c squared will be 3 times 10 to the power 18 squared. And an electron volt here, if you don't know, a mega electron volt is equivalent to 1.6 times 10 to the minus 13 joules. That's the conversion we're using here. So to work out the energy of each of the gamma ray photons, we can also work out the frequency of each. We will need to multiply the rest mass by 2, because we've got two of those particles, same rest mass for both, which gives us 1.022 mega electron volts. And we've got two gamma photons that are emitted. So for one of those photons, we need to then divide by 2 again, which gives us 0.511 mega electron volts, the amount we started with. Now, we can also work out the frequency of the photon because a photon is part of the electromagnetic spectrum, and we can work out its frequency. So the equation to do that is E energy equals hf, where h is a constant. It's known as Planck's constant. It's a very, very, very small, tiny constant, which is 6.63 times 10 to the power minus 34. So to work it out, very easy equation, we could just do the energy in joules. So we'd use that conversion factor over here and then divide that by Planck's constant to find the frequency, usually quite high because obviously gamma photons are the highest frequency of the electromagnetic spectrum. So if we can convert mass to energy, could we also convert energy to mass? Well, yes, we can. The opposite of annihilation also has its own name for converting pure energy in the form of a gamma photon into two particles, a particle-antiparticle pair, just like we see here with an electron and a positron. So this is known as pair production, which kind of sounds like what it should be, pair production producing a pair of particles, one anti and one regular particle. This occurs when a photon has enough energy, so it needs to have above a sort of threshold energy for this to happen. So to work out the minimum energy that the photon would need, you'd need to know the rest mass of these particles. Now, we're using the same two particles, but before it could be anything. It could be a proton and an antiproton. But anyway, you need 2 times the rest energy of one of those particles, which is 1.022 mega electron volts, and then convert it to joules, which gives us 1.64 times 10 to the power minus 13 joules. So that's the minimum energy the photon would need. You could work out the frequency again by using the same equation as earlier. That's it for leptons for now. Let's have a look at the right-hand side of this diagram and have a look at the hadrons. So hadrons can be split into 2 subcategories, baryons and mesons, but even these are not fundamental particles. They're all made from these things called quarks, which, to the best of our understanding, are fundamental particles, meaning they cannot be broken down into something smaller. So what are these quarks then? Well, these come in different flavors as well, just like our neutrinos. Now, the flavors are up, down, strange, and you can also have top, bottom, and charm quarks. Now, luckily for you at A-level, we're only dealing with 3 quarks. So we're not dealing with top or bottom or charm quarks. There's loads of history and interesting things you can learn about them, but they're not on the A-level spec. We need to know about up quarks, down quarks, and if you do AQA, you need to know about the strange quark as well. So first thing to note is that the key information I'm going to write down here in terms of their charge is all on your data sheet. So charge of each quark is fractional. The up quark is positive charge plus 2/3. Down and strange quarks both have a charge of minus 1/3. And we introduced this thing called strangeness. So up and down quarks have no strangeness. We don't have to worry about it. But strange quarks have a strangeness. And it's even stranger than that. They don't just have a positive strangeness. A strange quark has a negative strangeness of -1. These quarks also have antiparticles. So we signified that by drawing a little line above the top of the symbol. So U, D, and S now have a line above them to signify they are antiparticles. Now, as from earlier, the only thing that's different about an antiparticle is its charge. So the negatives become positive and the positives become negative. The strangeness of an anti-strange quark is also opposite. It is +1 strangeness. Now, something else we need to know about these quarks are their baryon number. So baryon number is another quantum number used to define these particles. And we'll come on to looking at why it exists in a second. But for now, the baryon number of all 3 quarks is 1/3. So 1/3. Now, protons are hadrons. They are also baryons. So we're going to figure out what quarks are inside a proton, because a proton isn't a fundamental particle. So we know that a proton has a baryon number of 1. It is a baryon. So therefore, it's got a baryon number of +1. We know a proton's got a charge of +1 and no strangeness. So what quarks could be inside? Now, if you're ever asked to figure out what quarks are inside something, it's kind of a bit of trial and error, just figuring out one stage at a time. And now, we usually look at the charge first. We need to get a charge of +1. So we definitely need some up quarks in there. If we put 2 up quarks, that gives us a charge of +4/3. So therefore, we put a down quark in it, gives us -1/3. Can't be a strange quark because it doesn't have any strangeness. So inside a proton, we have up, up, down. Let's then take on a neutron, which this time is a baryon. So baryon number of 1 has no charge and no strangeness. So we need to get a charge of 0. So if you put +2/3 an up quark, we would need 2 down quarks to make the charge be 0. So +2/3 -1/3 gives us 0. No strangeness, but it's 3 quarks, therefore its baryon number is 1. Now let's take a lesser known particle and a sigma particle. Now in exams, they could give you particles that you haven't heard of, but you'll always have enough information to figure out what they are. This sigma particle then, bit of a weird one. It has a negative charge, so a charge of -1. It also has a strangeness of -1, but it is a baryon, meaning it has 3 quarks in it. So what could be inside this then? Let's do a bit of trial and error to figure out what it must be. So we've got a combination of U, D, and S. We know because the strangeness is -1, we know it has to have a strange quark in it. So that's first up, -1/3. Now, to make the charge be -1, there's only one option really here, is that I need 2 more down quarks. So it's this quark composition of a sigma particle is strange, down, and down. Now, for antiparticles, you also need to figure out what quarks are in them. For antiprotons, is basically the opposite of what was in a regular proton. So an antiproton has a charge of -1, and an antiproton has a baryon number of -1 as well, instead of +1. So if we put our anti up, and anti down, that gives us a charge of -1 and a baryon number of -1. So that fits here for our antiproton. Now, one more quantum number you need to know about, going back to our leptons briefly, is this idea of a lepton number. So just like a baryon number, if anything's a baryon, it has a +1 baryon number. If it's an antibaryon, it has a -1. If anything is a lepton, it has a lepton number of +1. And if it's an antilepton, it has a lepton number of -1. If it's not a lepton, it just has a lepton number of 0. So our electron, muon, and tau and neutrinos have a +1 lepton number, and all the antiparticles have -1. The last category we haven't talked about yet is a meson. Now, a meson is not a baryon, so therefore has a baryon number of 0, but contains quarks. So the only solution to that is that it has a quark-antiquark pair, meaning it's +1/3 -1/3, giving it a baryon number of 0. So let's have a look at a few different common mesons and what's in them. So first of all, we've got the pions. We've got neutral, negative, and positive pions. And we've also got kaons, neutral, negative, and positive. Now, these ones, it's really useful to know. Pions don't have any strangeness, so can only be made up of up and down quarks and their anti-particle counterparts. Kaons do have a strangeness of either +1 or -1, so must have a strange or anti-strange quark in there somewhere. So let's deal with the pions first. I'm going to go right to left, just because it's a bit simpler to work out the positive and negative ones first. So positive kaons, we know it's positive. We know it's got 2 quarks. One must be an anti. So the only combination that would work with is if I have an up, so positive of 2/3, and an anti down, giving me a total charge of +1. Next, I could do the negative one. I need a -1 overall, so I do an anti up, so -2/3, and then a down, which is also -1/3, giving me -1. Now, a neutral one, you need a charge of 0. That could be an up anti-up. It could be a down anti-down to give you a neutral pion. So let's deal with these kaons. Now, for a neutral kaon, we know we're going to need a strange particle in there somewhere. So for a neutral kaon, that could be an anti-strange, so that would give us +1, and a down quark, which would give us a charge of 0. For a negative kaon, we're going to need a charge of -1, so that's again anti-up plus a strange quark this time. And for a positive kaon, that's a anti-strange quark plus an up, which gives us +1/3 plus 2/3, which is 1 overall. Okay, so these particles are all very unstable. They don't usually take very long to decay at all. Baryons generally are a bit more stable, like protons and neutrons. But for baryons, we've got the proton is by far the most stable one. So next we're going to look at how do these particles decay. And there are a few different conservation rules. Just like with conservation of energy, being that before and after has to be the same, in different decays and interactions between particles, there are a few things that have to be conserved. Charge has to be conserved. We also have to have the same lepton number before and after, as well as baryon number, and also energy and mass have to be conserved as well. Strangeness has to be conserved, but only in strong interactions, which we'll come on to what that means a bit later. So let's have a look at an example. So for any interaction, you could be asked to figure out, is it possible or not due to conservation rules? So let's have a look at this one here. This is a proton decaying to a neutron, a positron, and an antineutrino. So in an exam, you always want to write down below, like charge, lepton to a barrier, just do zeros, positive ones, and negative ones to show you know what you're talking about and is it conserved or not. So with a charge, we know the left-hand side is +1, neutral 0, positron +1, and antineutrino 0. So charge works out fine.
Baryon number, we know a proton is a baryon number, so +1 becomes +1 for the neutron, and then 0 and 0 for the electron and the antineutrino. And if we do lepton number, we got 0 on the left-hand side, but we've got an antilepton and another antilepton on the right-hand side, giving -2. So you then, therefore, you'd say the lepton number, the left-hand side, does not equal the right-hand side, so it's not conserved, so the decay is not possible. Let's look at a slightly different one. This one's involving a muon. So I've got, in terms of charge, -1 makes -1 plus 0 and 0. So that's fine. Lepton number, I've got +1 makes +1, -1 and +1, which looks like it is fine. So therefore the interaction is totally possible. So it is a legitimate interaction and decay that can happen. This is how the muon decays into an electron and 2 types of neutrino. Right, I mentioned the strong force, the strong nuclear force a second ago, so we're going to move on to talking about fundamental forces. Now, unlike push and pull and tension, these can all be explained by 4 forces that work on the subatomic level. The first force is the electromagnetic force. Now, you come across this before. This is why 2 protons repel each other, so it only affects charged particles. You've also come across gravity before. This affects particles with mass, although particles are very, very low mass, so we won't really consider it too much here. Then we've got the 2 we're really concerned with the weak nuclear force or nuclear interaction and the strong nuclear force or interaction. The weak nuclear force affects all particles, but the strong nuclear force only affects hadrons, so leptons cannot be affected by it. So even though it only affects hadrons, don't forget hadrons can be affected by weak nuclear force because it affects all particles. So hadrons can decay by the strong interaction, but also the weak more commonly. Now, how do these forces get mediated, or how do they get exerted? This is where the idea of exchange particles comes in. The analogy to use with exchange particles are 2 people on skateboards facing each other, and one of them throws a basketball at the other. Now, if nothing else changes, the 2 people will become slightly further apart because of Newton's third law. The person throwing the ball will move backwards, the person catching the ball will also move backwards. Now, while this obviously isn't exactly what happens with exchange particles, it occurs in the same way, for example, when 2 electrons repel. So exchange particles are virtual particles that are transferred between 2 different particles that allow a force to be mediated or exerted. Now, each of these 4 forces have different exchange particles. For the electromagnetic force, it's a photon. For gravity, it's called a graviton, even though we don't really know they exist yet. It's very much a hypothesis. Gravity is a very, very weak force, so it's a lot harder to discover things about it. Then for the 2 we're interested in today, we've got the weak nuclear force, which has 3 types of boson, which it can have as the exchange particle. We can have W minus, W plus, or Z0 or neutral Z boson. And for the strong nuclear force, it can either be a pion or a gluon. Now, different decays we've looked at so far, we can represent using Feynman diagrams. So with a Feynman diagram, they look kind of scary, but they are basically just a pictorial way of showing a decay. So let's say our beta minus decay from earlier, I've got a neutron changing into a proton plus an electron and an antineutrino. So how to show this on a Feynman diagram, we go upwards to go up on in time. So we start off at the bottom, and we also make sure we kind of give particles their own space. So we start off with our neutron, change it into our proton. We keep that on the left-hand side because it's still a hadron. And then we have our exchange particle, which kind of wiggles off to show it's a virtual particle that turns into our electron and our antineutrino. Now, in this case, the exchange particle is the W minus boson, and that's because once the neutrons change into a proton, it needs to take away the remaining negative charge for conservation of charge, which then becomes the electron and antineutrino. So this is an example of a weak interaction decay because it is affecting all particles are involved. Changing this to beta plus decay, so we change the proton to a neutron, neutron to a proton, and this time it's a W plus boson that's carrying away the positive charge to make the positron and the neutrino. Now, just a quick note on antiparticles. Some textbooks show the arrows pointing the opposite direction. It's not required for A-level specifications, but just so you're aware. Now, one last thing about Feynman diagrams, you quite often find the baryons always on the left-hand side and the leptons on the right-hand side, just to distinguish between them. So other types of Feynman diagram you can have. So when 2 protons repel each other, you can also represent that on a Feynman diagram, showing the 2 protons at the start and at the end moving away from each other, and there's a photon exchange between them to show that a force is being exerted. Now, in this case, obviously, you've got two baryons on left and right side. That's because there's no leptons occurring at all. Now, electron capture, which is when a nucleus captures an electron from an inner shell of around the atom, is when a proton and electron we start off with, so going from the bottom, and now the proton changes into a neutron and the electron changes into a neutrino. Now, in this case, the exchange particle, so between those two particles, is a W plus boson. Now, please be aware, you could be asked for other diagrams than this. I would definitely learn the neutron decay, the proton decay, electron capture, and two particles repelling. But if you follow those rules, you can do it with any sort of particle interaction, really. Now, the last thing to note about the strong nuclear force is how it actually holds the nucleus together. Now, this is really fundamental to understanding why nuclei exist in the first place. So the strong nuclear force, if we were to draw a graph of the distance from the center of the atom, so right at the center, and put on the y-axis the strength of the force with repulsive above the x-axis and attractive below it, we find that actually the strong force is repulsive below 0.5 femtometers, and it gets attractive between 0.5 and roughly 3 femtometers, and after that basically becomes zero. So if you ever wondered why protons are held together with the neutrons in the nucleus, why don't they repel? It's because for those very, very small distances, the strong nuclear force is attractive. Now, you might be asking, well, what about the electromagnetic or the electrostatic force? Well, we're going to come to that in a second. But don't forget, the strong nuclear force is responsible for keeping the nucleus together. Now, you might be asking, well, what about the electromagnetic or electrostatic force repelling those protons? Well, that is at play as well. However, at those really, really small distances, the strong nuclear force is bigger. However, the bigger the distance you get, that means electromagnetic force becomes bigger than the strong nuclear force. So that explains why, if you have really big nuclei, they don't really survive for very long. They repel really quickly, so it usually decays or could undergo fission, and you don't get really big nuclei. There is an upper limit on how big a nucleus can be. Right, we're almost there. The last thing to talk about is specific charge. So specific charge is one of those weird equations in A-level physics you don't get given on your equation sheet, but it's quite a nice one to remember. It is the charge per unit mass of a particle. So meaning you divide the charge by the mass to get the specific charge. Charge in coulombs, mass in kilograms, specific charges in coulombs per kilogram. So you usually get asked this question of a nucleus or an ionized particle. Obviously, a normal atom wouldn't have a charge, so it wouldn't have a specific charge. And please make sure you use the data sheet for all your values, for example, to work out the charge or the mass in kilograms. Now, the specific charge of an electron is much bigger than a proton because it has a much smaller mass. That's a good fact to know. The electron has one of the largest specific charges you can get, and the values for specific charge are normally in the order of about 10 to the power 7 coulombs per kilogram.
Are you made up of waves or of particles? Now, this fundamental question about the nature of reality divided physicists for decades around the turn of the 20th century, and there were numerous different opinions about which was the most accurate view. But quantum physics tells us that matter can be both. So light we know is a wave because it can diffract. This was very early established. When you were to put it through a small slit similar to its wavelength, you have a diffraction pattern formed. But it can also be considered to be a particle, and that's due to this thing called the photoelectric effect, which is what we're going to look at today. So the photoelectric effect can be demonstrated using what's called a gold leaf electroscope. So it is this vacuum chamber which has these gold leaves hanging down from the top that are connected at the top but separate. And what we noticed is that if I was to shine light, so just any color light, onto the top surface, nothing really happens. However, if I was to shine ultraviolet light onto that surface, both of the leaves would start to separate. Now, the reason for this is because they have opposite charges, so they're repelling. Now, this has been demonstrated by using sort of static electricity as well, by using sort of charged rods. So we know this is definitely true. But the question is why? Why is it suddenly becomes charged when you shine ultraviolet onto the surface, but don't shine a light onto the surface? So it's all due to this thing called the photoelectric effect. Now, photoelectric effect is if I was to zoom in on the surface of the metal and shine ultraviolet light onto the surface of it, what we'd find is that actually you have these electrons being emitted. So the definition for photoelectric effect is when electromagnetic radiation with enough energy is incident onto a metal, you have electrons that are emitted from the surface. Now, the key parts in there is that it's the surface of the metal, so not deep down, and it's got to be radiation with enough energy, which is the difference between UV light, which we were just talking about, and sort of regular visible light. UV has a higher energy and a higher frequency. So if I do it with regular light, visible light, it just doesn't work. Nothing happens at all. So going back to the electroscope then, what physicists noticed was that when the electroscope is charged originally and you shine ultraviolet light on it, you actually find as well that the leaves will go back to their original position. Now, this is because electrons are being emitted from the surface of the metal, so therefore the whole gold leaf becomes uncharged because the electrons sort of go upwards towards the metal and become emitted because you're losing those electrons. So if you lose those electrons, that meant it was negatively charged to begin with, and now it has no charge, so there's no reason for the leaves to separate, so they go back to where they were before. Okay, so considering the whole electromagnetic spectrum, we know we've got radio waves, microwave, infrared, visible lights, UV, X-rays, and gamma rays. We can see here from my very poorly drawn diagram that UV has a higher frequency, which means it has a higher energy than visible light. And obviously X-rays and gamma rays also have a much higher energy because they have a higher frequency as well. So there's this threshold frequency that EM radiation needs to make photoelectric effect happen. And we define that threshold frequency as the minimum frequency electromagnetic radiation has to cause electrons to be emitted from the surface of a metal, or basically to cause photoelectric effect to happen. Now, as well as that, there's this idea of the work function, which applies to the metal itself. And the work function is the minimum energy required for an electron to be emitted from a metal surface. So the threshold frequency applies to the EM radiation coming in. The work function applies to the metal. They'll all have a different work function because they have slightly different sort of atomic structure in them. Okay, so this is all well and good, but how does it go about explaining how light can be considered a particle? So the explanations for photoelectric effect, before quantum physics came about, we had sort of classical physics, which is sort of Newtonian mechanics, things like that. One of the things it would predict was that the emission of these electrons depended on the intensity of the light or the brightness of the light, not on its frequency. We know with a quantum explanation that emission doesn't depend on its intensity, but it only depends on the frequency of the EM radiation. So it doesn't matter how bright you make it, regular light won't emit those particles. Another thing that classical physics predicted that wasn't correct was that the emission would increase sort of gradually over time, whereas quantum physics sort of helps explain that it emits sort of instantaneous. Once it reaches that threshold frequency, it goes from 0 to millions of electrons in a second. So how does the idea of what light behaving as a particle help explain this? If we consider light to be photons, so these photons of light are particles of light instead of a wave, what we notice if we have a photon of light coming in, giving that electron the energy, it's a 1-to-1 ratio between the photons coming in and the electrons being emitted. Now, it doesn't really make sense if you consider light to be one continuous wave. It has to be in these sort of discrete packets or these discrete particles for this to make sense. Now, one thing to note is that the intensity of the light does affect something about the emission of electrons. It's that once you reach the threshold frequency or you reach the work function, the intensity is proportional to the number of electrons emitted per second. So once you reach the threshold frequency, more intensity means more electrons emitted, but they don't have more energy, there's just more of them. So you might remember this from a particle physics video. If I was to look at the energy of a photon, it's given by Planck's constant times by the frequency, where each Planck's constant is equal to 6.63 times 10 to the minus 34 joule seconds. So using this equation, we can sort of formulate a new equation for photoelectric effect. So basically, if that's the energy of a photon, HF, if that's equal to the work function, so the minimum energy required, then we have emission occurs. If it is slightly less than, there's no emission occurring, okay? So HF is less than the work function, even by a tiny amount, you have no emission at all. But what if it's a fair bit greater than the work function? Where does that extra energy go? So if HF is greater than the work function, what happens is the electrons are given extra kinetic energy. So the energy doesn't disappear, goes into those electrons emitted from the metal, which is given to them as kinetic energy. So combining all these things together, this is the general photoelectric effect equation. HF is equal to the work function plus EK max, where EK max is the maximum kinetic energy given to those electrons. Okay, now if you were to plot a graph of increasing frequency and the kinetic energy of those electrons, it would look something like this. Now I'll talk about how you go about measuring the kinetic energy of those electrons in a little bit. But there's a couple of features of this graph we need to take note of. So generally speaking, energy is proportional to frequency. Now we've got an x-intercept here, which is a bit unusual, but this is equal to the threshold frequency. So when the EK max is 0, i.e. when you've just gone off energy to emit those electrons, then the frequency must be the threshold frequency. Now, if I work backwards and extrapolate back to the y-axis, I can also note that this is going to be equal to the negative of the work function. Now, negative of the work function doesn't have any physical significance, but it does allow us to find it from the graph, and then we can work out what the work function is. Now, putting this equation into the form y equals mx plus c, so I've got EK max equals HF minus work function, and we can see if I've got EK max on my y-axis, if I've got frequency on my x-axis, that means that plus c is going to be equal to, so my y-intercept is going to be equal to negative the work function, and m is going to be equal to Planck's constant. So it is a method of calculating Planck's constant using the photoelectric effect. So how you can kind of incorporate these into a circuit and measure the amount of electrons and the energy they have is by using something called a vacuum photocell. So it looks a bit like this. In a diagram, you just find it's got a photocathode, which cathode is a negative part of the circuit. You have incident EM radiation. Now, the idea is if you were to detect a current on the ammeter, that's because there's a photoelectric effect occurring from the photocell, which means electrons are emitted from the photocathode. Now, these electrons will then travel around the circuit and become detected by the ammeter, which detects current. Now, usually, even though it's an ammeter, we're going to say it's a microammeter here because it's going to detect very small amounts of current. It's not going to be much current detected at all. Now, the intensity is proportional to the current. Like I said earlier, if the EM radiation has a high enough energy, bigger than the work function, then that means that a photoelectric effect is going to occur. If you were to make it brighter or higher intensity, you'd have more electrons, which means a greater current. Now, how do we measure the energy of these electrons? Well, it's by using the idea of a stopping potential. So stopping potential, as a definition, defined as the minimum potential or voltage needed to stop photoelectric emission. To stop photoelectric emission means that the kinetic energy of the emitted electrons becomes 0. So it only happens when HF, the photon energy, is equal to the work function. We do this using an electric field. So when you apply an electric field, you do work on the charged particles, which equals to charge times PD. And in this case, the charge is the charge of the electron, which is 1.6 times 10 to the minus 19. So therefore, the work done here is equal to E times by Vs, which is the stopping potential, which you can then use to work out the stopping potential as you know the charged particle. So let's say we've got an electron hits an atom, bumps into one of those inner shell electrons, and it leaves the atom, becomes ionized, therefore it's got a positive charge. Now, what if the electron coming in doesn't quite have enough energy to do that, but has enough energy to promote that electron to a slightly higher orbit? In that case, it's not ionized, it's not lost the electron, but what we'd say is the electron's now become excited, as it's been promoted to a higher energy level, and it's in an excited state. So we can change the way we draw this diagram to make it a bit easier to understand what happens with excitation, and then also what happens with de-excitation when the electron comes back down. So instead of having this sort of circular pattern of electron shells, we draw them sort of side on almost, like you see here. Now, the first thing to note is that the bottom of this diagram is the ground state. That's the lowest energy level that an electron can hold. And this time we're going to talk about, instead of an electron being incident, we could have this effect occurring with a photon of EM radiation incident on the atom. So when that happens, the electron gets promoted to a higher energy level, which, as we talked about, means it's excited. Now, instead of that, it could also go to the 2 levels up or 1 level up, just depending on the amount of energy that it's given. Now, it has to be these discrete energy levels. It can't go sort of halfway between one level and another. It just can't happen. It just wouldn't move at all in that case. Now, this is really important to understanding the quantum nature of matter. So if we consider the photon to be a particle, it has this discrete amount of energy, and the electron itself cannot go between energy levels. It can only increase by a discrete amount, which if you want a bit more detail on, check out my video about wave-particle duality. So what goes up must come down. The electron will eventually de-excite, which means it will go from a higher energy level to a lower energy level after a very short amount of time, which is usually about the order of microseconds. So if it's got to the second level up, it can either go back down to the ground state, or it can go to the next energy level down. Now, as that happens, it emits a photon. Now, that's because energy can't just sort of be absorbed. It can't go anywhere. It can't just disappear. It has to be emitted in another form. So we have a photon of EM radiation emitted. So that could be an X-ray, it could be a photon of visible light, anything really. Now, if we include the idea of another energy level here, which isn't really another energy level, it just means you've got enough energy to leave the atom. That would be called the ionization level. Now, all these different levels have different energy values associated with them. So in this example here, I'm going to write down some values which are getting lower, but they're getting more and more negative, which I'll explain why in a second. And they're in the units of these things called electron volts. So the reason why they're negative is because if an electron goes from a ground state to a higher energy level, it has to gain energy. However, it can't just gain sort of infinite energy when it leaves the atom. So it has to therefore be negative the sort of further down the energy levels we go to the ground state. Now, hopefully you know how to define the electron volt. It comes out throughout particle physics and quantum physics quite a lot. So it's defined as the kinetic energy gained by an electron when it's accelerated through a potential difference of 1 volt. So imagine I've got 2 plates here, one with 0 volts, one with 1 volt. We've got an electron that goes from one side to another. It's going to gain an amount of energy. Now, work done equals QV. Q is charge. So for an electron, we write the small case e to indicate it's 1.6 times 10 to the minus 19. And the voltage is 1. So therefore, the amount of joules it gains is 1.6 times 10 to the minus 19 joules. So this is a unit of energy. To convert from electron volts to joules, you need to times by that value, 1.6 times 10 to the minus 19, and joules to electron volts, you divide by it. My way of remembering it is electron volts to joules go up in the alphabet, so you times joules to electron volts, you go down in the alphabet, so you divide. Now, to work out the frequency of any photons that are emitted by de-exciting, or the ones that are needed to excite an electron, we need to use the equation E equals HF. And now we're going to modify it slightly to say E2 minus E1, or the difference in energy, equals HF. But it's the same thing really. And that difference has to be in joules. So you have to be able to convert these electron volts to joules. So let's have a look at an example here. So let's say we got the transition from the ground state, so minus 11.8, goes up to minus 7.2. So if I'm then going to find the difference, that's a difference of minus 4.6 electron volts, which then I can use to find the frequency. But first of all, before I do that, I need to convert it into joules. So in this case, timesing by 1.6 times 10 to the minus 19. So to work out the frequency, I've got that value divided by Planck's constant, which is going to give us a frequency of 1.1 times 10 to the power 15 hertz, which sounds reasonable. That's roughly the frequency that gamma ray photons have. So that would sort of make sense here. It's within the electromagnetic spectrum, the highest end of frequency end of it. A really common example of these energy levels of electrons being used is in fluorescent lighting or fluorescent tubes. So these are different to LED lighting. These are tubes that you find they could be different colors, and you supply a voltage or a PD to them, and they glow basically. So how do they work? Well, we have a setup a bit like this. I know this looks like a bit of a weird circuit diagram. We've got a main supply. Now that's going to essentially give energy to these atoms inside some mercury vapor. So you need this mercury vapor inside the fluorescent tubes to be able to work. So power supply gets switched on. The mercury atoms are given energy. Now, when they're given that energy, even though it's from the voltage of the circuit or the PD of the circuit, the same thing happens. The electrons will excite, and then they'll de-excite quite quickly. Now, when they do that, just because they're made of they're mercury atoms, they happen to emit UV photons when that occurs. So these UV photons, what happens then is they go into the second sort of part of the tube where there's a fluorescent coating. Now, this fluorescent coating is designed to absorb these UV photons, and rather than re-emitting as UV, they actually get re-emitted as visible light, which we can see. That's why it's fluorescent. It's giving off light when you supply it with electrical energy, or PD. So these are absorbed by the fluorescent coating. These coating atoms excite, then de-excite, and emit visible photons, which then we can see come out at the end of the fluorescent tube. So in summary then, we've got PD gets supplied. The mercury atoms will excite and de-excite, emitting UV. And then the fluorescent tube will excite and de-excite, absorbing UV, but re-emitting visible light. Now, this is a really good example. If you ever get asked, or if you ask, do I need to know about this at A-level physics? For the AQA specification is specifically mentioned on the specification. So it is definitely worth knowing how anything on the specification works, but absolutely things that are mentioned specifically. One really important application of electron levels and their transitions is absorption and emission spectra. This can allow us to see what kind of atoms and what kind of elements are in distant gases and help identify them. So if I was to shine white light through a gas, what I'd find is if I were to have all the different colours of the spectrum split up on the other side, what I noticed, so the light got shone through the gas, will have certain wavelengths become absorbed by those atoms in the gas. Now it's only certain wavelengths because, as we looked at previously, atoms only have certain energy levels that electrons can travel up to when they absorb different energy photons. So when those atoms sort of de-excite, and they'll re-emit maybe a different color light, but there'll be a dark line on the spectrum of colors visible. And each of those lines corresponds to a specific element. So let's say we've got 3 dark lines in a certain spot. I might know it's got hydrogen in it because hydrogen atoms absorb those specific energies of those specific wavelengths. So this allows us to see what element is in the gas, which is really important because all these atoms have specific energy levels. Sometimes we don't know. It's one of the ways we have of identifying it, sometimes called spectroscopy. Now, the inverse of this is an emission spectrum. So the explanation is fairly similar, but for this, you have a hot gas. We're not shining light through it, but it's emitting sort of light 'cause it's so hot. And you'd have it only emitting certain wavelengths. So it's a dark spectrum apart from certain lines. So in this case, we would say the light shone is emitted by a gas, has certain wavelengths that are emitted due to atoms sort of de-exciting and then emitting these photons. So this causes bright lines to be formed throughout a sort of dark spectrum, basically, and does a similar thing, but allows us, instead of telling what elements are being what elements there are due to wavelengths being absorbed, it allows us to see what elements are in distant stars and planets by the gases near their surfaces and in nebula and things like that, which is really amazing, a really fun application of these ideas in quantum physics. Is matter a wave or a particle? Now, we knew light could be considered as both because by that point we knew it was a wave from diffraction, but it could be considered a particle from the photoelectric effect. And Louis de Broglie said, well, actually, if that's the case for light, why can't the reverse be true? Why don't we take matter like electrons, which we know are particles, because they can be deflected in an electric or a magnetic field? What about if we were to consider them as waves? What evidence would we expect for that to happen? So to be considered as waves, we have to see if they would diffract. So one of the experiments done around this time was to take different size slits and to fire electrons really, really fast through them and see what happens. Now, if waves were a particle, what we'd expect to happen is just to get sort of 2 piles of electrons be detected by a detector. However, if they were waves, what we'd expect to happen through a single slit or a double slit is interference patterns to occur with constructive and destructive interference happening, causing these bright maxima and these darker minima to happen, just like we find with waves. And this is what we found. So electrons were proved to be behaving as waves when they were fired fast enough to be able to diffract. De Broglie called these matter waves, and he said we can work out their wavelength by dividing Planck's constant, so 6.63 times 10 to the minus 34, divided by the momentum of the particle, or its mass, multiplied by its velocity. So the mass of the electron, and we can't really affect at all because it's a fixed thing, but it does imply that to have a non-negligible wavelength, you have to have a very, very low mass particle. For example, for a human being, the wavelength is around about 10 to the minus 35 meters, just because our mass is so much bigger than an electron. Whereas the wavelength of an electron is, roughly speaking, 10 to the minus 15 meters, which is still very small, but it's of the order of atoms. So it is observable that it can diffract. So the experimental setup for these electrons was to have them shone through a metal sample. And what they noticed was, instead of in 2D, these kind of dark and bright fringes, you actually have these circles being formed where you've got interference basically in 2D with a central maximum, then a gap where it's a dark spot where it's a minimum and maximum, minimum, etc. But this time in a ring rather than sort of in a fringe pattern as you see with light done in 2D. Now, the idea is behind this metal foil, the gaps are around about the size of 10 to the minus 15 meters, or 10 to the minus sort of 13, 14 meters, which would then be able to show, if electrons could start to diffract around them, that electrons actually have that wavelength, which we calculated earlier. So first thing is to draw out our wave and start to label it. Now it's going from left to right, so all points on the wave will oscillate up and down and the wave will travel left to right. Now if I've got my x-axis is time, that means the distance between one peak to another is known as the time period. Okay, and the time period can be defined as the time for one complete wave or one complete cycle. Knowing that, we can also use it to define the frequency. So the frequency of a wave is given by 1 divided by the time period. And frequency is the number of waves or number of cycles in 1 second. And we should know that is measured in hertz or seconds to the -1. Now we've got the equilibrium point to the maximum displacement, which is the amplitude. And that's how we define the amplitude. The amplitude is equal to the maximum displacement. So displacement meaning the distance in a straight line between the equilibrium point and where the particle is. So the maximum displacement is refers to the amplitude. Now, because it's a progressive wave, that means it moves. So in this case, we're moving left to right. So the particle that we see on the screen are going to be moving up and down depending on whether the wave has a peak coming up to them or a trough coming up to them. So all particles oscillate to the maximum displacement just at different times, which is not the same on a stationary wave, which you can see in my other video to find an explanation of that. So the wavelength, and we should know this from GCSE, is the shortest distance between two particles or 2 points on a wave that have the same displacement. Okay, so I can't label it on my graph here because I've got time on my x-axis, but if I did have distance or displacement, I was talking about a wave, I could label it there instead. Next, let's look at the wave speed equation. So the general equation for speed is equal to distance divided by time. Now we're going to talk about just one cycle and the distance and the time taken for that one wave cycle to take place. So the distance of one cycle, as we've just mentioned, is known as one wave is known as the wavelength. So wavelength is going to be our distance. Now the time taken for one wave is going to be the time period, so capital T. Okay, so I've got time for one wave and distance. Now, instead of time, I can write down 1 over frequency because time period equals 1 over frequency. And if I divide by a denominator, that means I can put it on top. So speed, which you usually use the letter C for instead of V, is given by frequency times wavelength with the units given there on the screen. So that's our labeling and definitions done. Let's talk about something that happens with progressive waves, which is called polarization. Now, this polarization, this effect, only happens with transverse waves. So we're going to talk about the difference between transverse and longitudinal first. So transverse waves means it has oscillations that cause the wave are perpendicular or right angles to the direction of energy transfer or to the direction of the propagation of the wave. For longitudinal, oscillations are parallel or in the same direction as the direction of energy transfer. So you do need to know some examples for each of these as well. So examples for transverse wave tend to be light and anything on the electromagnetic spectrum. Longitudinal, there's less of them example-wise, but you've got sound, you've got ultrasound, you've got P waves for earthquakes, and that kind of thing. Now, the easiest demonstration of this you might have seen is on a slinky or something similar, where if you push it from left to right, the wave moves left to right. You have these compressions traveling down the wave, whereas if you're trying to demonstrate a transverse wave, if you move it up and down, the wave will still go left to right. This time it's at a right angle to the oscillations that caused it. Okay, now, as I mentioned earlier, we're only going to talk about transverse waves when we talk about polarization, and that's because transverse waves can be polarized, and they're the only type of waves that can be polarized. You cannot do it with longitudinal waves, and I'll explain why. Now, I've got a slightly tricky task to draw a diagram of this. I'm going to draw some unpolarized waves. Now, this is deliberately not going to be great. You can find a better image I'm going to put on the screen as well. But the idea is they're oscillating in all directions, so up, down, left, right, diagonally, etc. It's easier to demonstrate if you look head on. So if I look head on at the wave, I'd find they might have oscillations up and down. They might have some from left to right. And might have some in diagonally as well. And even though I can't draw in the diagram, they are in all directions. Now, this is what's known as an unpolarized transverse wave. Okay, so an example of that would be an electromagnetic wave. Now, the definition would be that there's vibrations or oscillations are in all planes, or it's vibrating or oscillating in all planes of directions, basically. So plane is a fancy word for direction if you weren't sure. Now let's look at what happens when what we need to do to polarize these waves. So to polarize it means I'm going to limit the oscillations to one plane or one direction only, just like these blue ones here. So the definition would be vibrations or oscillations are in one plane only. Okay, so looking at head on, I've just got the left to right ones here instead of up and down, and that's also known as plane polarized. And this one would be horizontally polarized because I've let the horizontal plane through. Instead of the vertical one, I could do that as well, and that would be vertically polarized light or vertically polarized wave. Now, how do I go about achieving this? Well, it's due to something called a polarizing filter. So polarizing filter obviously doesn't look like this. You might see one in school. Generally, they look like dark pieces of kind of perspex. In this case, it's designed just to let those vertical planes of wave through, or vertical oscillations through. Now, where might you use this? Why is this important? Well, this is the kind of technology that's used in Polaroid sunglasses, which reduces glare. And the glare means the light that's reflecting off bodies of water, so lakes or the sea, etc., which tend to be polarized. So if they're polarized in one direction, your Polaroid sunglasses let through the other direction, so they don't let through as much glare. And it reduces the light intensity in that case. And it reduces the overall intensity as well, not just the glare. You might find them also, you'd find them also in satellite dishes, which have to be aligned in the correct direction for radio waves to be transmitted and to be received successfully. Okay, so that's polarization. Let's have a little look at phase difference then, or phase in general, which comes up multiple times in A-level when we talk about waves. So let's draw a wave on the screen again. This time I've extended it a bit. I've got some notches so I can draw a second wave on. Now this second wave, you might notice, looks similar to the first wave, but it's kind of shifted to the right a little bit. Now what we say is those two waves are out of phase with each other, and we'll talk about what that means in a second. Now in terms of how far out they are out of each other's cycles, hopefully you guys can see it's a quarter of a cycle difference. Okay, so it's a quarter of a wave, then one starts. Now, when we talk about phase difference, we need to compare waves to circles, and here's a really helpful GIF that can help explain it, or picture that help explain it. So when we talk about phase difference, we're going to consider a wave to be one circle. So instead of saying a quarter of a cycle, we say a quarter of a circle in degrees, which is 90. If I was to draw another wave on, and we've got this wave compared to the blue one, it's going to be half a cycle out. It's exactly opposite, and it's 180 degrees out of phase with my original wave, which is half a circle, because that's half a wave. Now, instead of saying degrees, we can also talk about radians. Now, if you do A-level maths, you should know about radians already. Now, radians in a circle are 2 pi in total. So that means for 90 degrees, a quarter of 2 pi is half pi, or pi over 2, and half of 2 pi is pi radians. Okay. I've also got a little link up here to how to convert between them. So you times by 2 pi over 360, or to convert radians to degrees, you times by 360 divided by 2 pi. As the name suggests, stationary waves are in fact stationary. The energy is localized into one location, but how are they formed? So in this video, we're going to look at definitions behind stationary waves, how can you identify different features, and the equations as well. So a stationary wave, you might have seen this practical done before, a piece of string with a vibration generator and a signal generator. The vibration generator generates these waves that travel to the one end and reflect back, and they form shapes like this. So how are stationary waves formed? Well, they're formed when you've got two waves that are traveling in opposite directions. Now, on the string, that means it's reflecting back. It doesn't have to be like that, but they're traveling in opposite directions in the same medium. So in this case, we're talking about on the piece of string. It could be in air for sound waves. It could be anything. And they're in the same medium, and they have the same frequency. So these waves are produced by the same signal generator, so they have the same frequency, for example, 20 hertz. Now, stationary waves form these interesting patterns on that piece of string due to something called superposition, which comes up a lot in physics. It will come up in optics as well. Now, superposition means if you combine waves together like this, the amplitude will increase because the waves are in phase, or their peaks exactly match up. So what we'd say is their amplitude reinforces, the two amplitudes reinforce when they are in phase, i.e. the amplitude doubles in this case. Okay. Now, another name for that kind of similar effect is constructive interference, meaning when those two amplitudes reinforce. Now, the other thing that can happen is if they are not in phase, if they're out of phase by half a wave, then it's called destructive interference, and the amplitudes are cancelling. Okay, so they're either pi radians out of phase or 180 degrees out of phase, meaning there's a flat line there. There is zero amplitude. So that's why we get these different shapes. Then, if I talk about the point in the middle where there's no amplitude at all, that is the point where there's destructive interference occurring because there's no amplitude, the wave's not moving. Whereas the points at either end are the opposite, they are reinforcing. Now, the points where there's no displacement is called a node, N-O-D-E. A good way of remembering it, node, no displacement. And the parts where it's maximum displacement is the antinode, so kind of like the opposite. Okay, so that's maximum displacement antinodes, and there are two in this image where the wave travels at its maximum amplitude. So stationary waves in general are very different to regular progressive waves in that not all particles oscillate with the same amplitude. If you're in the ocean and a progressive wave comes past, you go up, you go down. These particles are not like that. The energy is localized and the particles either oscillate with zero amplitude or maximum amplitude or somewhere in the middle, but it doesn't change. And the other examples of these, you might find microwaves, ovens have stationary waves in them, also musical instruments using sound and things like that. Okay, so that's our features looked at. Let's have a look at what we can describe this shape of wave here, which is called a fundamental frequency. And let's say it's at 10 hertz. Now, another name for this is called the first harmonic, and they mean literally the same thing. And you've got a wave pattern, which is just that one loop. Now, what if I was to double the frequency? Well, in that case, you'd get a shape that has two loops on it, just like the one from earlier, where you've got one node in the middle and two antinodes at either end. Okay, so this doesn't have a fancy name. This is just called the second harmonic when I've got two loops instead of one on the same length of string. If I was to increase the frequency even more, this time to 30 hertz, I'm keeping the numbers simple here. If I triple the original value of frequency, I'm going to get the third harmonic, which means three loops on my piece of string. I've got three antinodes, I've got five nodes because I've got one at each end as well. Now, you could go on with this. You could talk about the fourth harmonic, fifth harmonic, etc. But each time you need to be aware of how many wavelengths there are on the piece of string. Now, up, down, and up again is one wavelength, just like on the image. So what that means is that the second harmonic is a whole wavelength. Third harmonic is actually 1.5 wavelengths. And that means our first harmonic is half a wavelength overall. So what we can then generally say is the distance between adjacent nodes, so those points of no displacement, is equal to half a wavelength. So if you use that rule, you can do that for any amount of harmonics, even if it's like 15 or something ridiculous like that. Now, let's say we've got the length of this string measured. So generally speaking, we can use our wave speed equation to adjust it slightly for stationary waves. So speed equals frequency times wavelength. Here, instead of wavelength, for the fundamental frequency, that is going to equal 2 times the length, because I'd have to double it to find a full wavelength. Now, there is a big, long equation to work out the fundamental frequency of our stationary waves, and it looks a bit like this. So frequency equals 1 over 2L, where L is the length, all in the square root, tension divided by mass per unit length. So tension is a force measured in newtons, mass per unit length is in kilograms per meter. The tension is provided by the weights at the end, so almost always that's going to be mg with this particular setup. And it's worth using this equation to be able to work out what the relationships are between these factors. So you could be asked to plug numbers in, so make sure you know how to do that. But examiners love asking with this kind of equation, well, if one thing's changed, how would the other things change? So let's say the tension goes up by a factor of 4. How would the fundamental frequency change? Well, if I put this up by a factor of 4, it's within inside a square root. So to find out how much the frequency changes, I just do square root of 4, which means the frequency doubles. Let's say I was to change the length this time by a factor of 4. How would the frequency change? Well, these two are inversely proportional. So 4 times the length means the frequency goes down by a factor of 4 or by a quarter. So that's how that relationship would work. Lastly, we're going to talk about is phase. So phase on a stationary wave is easy once you get your head around it, but it's a bit different to progressive waves. Let's say I've got these 2 points here. So these 2 points are between adjacent nodes, i.e. they're between 2 nodes. What is the phase? Well, they're in phase. They're going to go up and down at exactly the same time period, exactly the same velocity as each other. So they're in phase. If I've got 2 particles that have a node between them, they are going to be in antiphase. That means that they're pi radians or 180 degrees, and it means that one goes up, the other goes down exactly. So first of all, what is diffraction? Well, diffraction is when a wave spreads out when it travels through a gap that is similar to its wavelength, like in this diagram here. So the gap here is similar to its wavelength. So after the gap, it will spread out. And this is really useful because it is demonstrated by light traveling through very, very small gaps. And it also helps explain why sound can be heard round a corner or through a door where light can't, because the wavelength of sound is much, much bigger than the wavelength of light, roughly of the same order as a doorway. So talking about, centimeters, meters, as opposed to light, the wavelength is hundreds of nanometers. So you have a very, very small gap for light to be able to diffract. Now, this is a huge deal in the 1800s because this is evidence of light being a wave, the fact it can diffract. Only waves can diffract, particles cannot, which was one of the kind of abiding theories at the time, which eventually visited in quantum theory. So let's have a look at this idea of the double slit. So we've got a light source here, which in the 1800s would have just been a lamp of some sort, and it travels through a single slit, then goes through a double slit, then travels to a screen, and there's a pattern seen on the screen. Now, the pattern we get are these even dark and bright fringes, or dark and bright spots that are even in width, even in intensity, and we need to be able to explain them. So let's have a look at the bright and dark fringes first of all that are observed. Now, first thing to note in this setup is the light coming through the single slit. The reason there's a single slit there first is so that light is coherent. That means all the light traveling through the single slit has exactly the same frequency and has a constant phase difference. Not in phase necessarily, but a constant phase difference. Now, when it travels through a double slit, this drawing is not going to be perfect, but the waves will overlap. And when they reach the screen, an effect known as superposition happens. Now, this can lead to one of two things. When you have the bright fringes, that means the waves meet in phase with each other. So a peak meets up with a peak, which is also known as constructive interference. This means the amplitude is doubled effectively, meaning the fringe is bright. At the dark spots, the waves meet in antiphase, or in 180 degrees or pi out of phase. So this means it's called destructive interference, and that means a peak meets a trough, which means they cancel out with each other. So just like in the diagram here, the two peaks line up, means the amplitude is doubled. If the peak meets a trough, that means the amplitude is zero. That means it's a dark spot. This effect overall is known as superposition, and those are the two things that we come out of the bright and the dark fringes. And those fringes, like we said, are even intervals and they have the same intensity throughout. So let's have a closer, more detailed look at the setup and see if we can derive an equation to help explain, well, how does the fringe spacing vary, what affects it. So we've got two slits we're going to call a slit separation S, and we've got the double slit to the screen. The distance between those two is capital D, and W is the distance between the center of the central fringe and the center of the first fringe. We're just looking at those two fringes for now. Okay, now it goes without saying, all these quantities will have to be in meters to be able for this to work. Okay, now we're going to derive this equation using the idea of similar triangles. So first triangle we're going to draw is this one. So the two rays from each slit will meet up at that first fringe. Just looking at that one for now. And that will form a triangle, which we're going to sketch out properly in a second. But it's really important to note is that those two waves must be in phase. Half difference of those two waves has to be one wavelength. For each fringe, it has to be a whole number of wavelengths. For this first fringe, it has to be one wavelength difference because the peak has to meet with the peak of the other. Now, before we have a look at these triangles, we're going to use something called the small angle approximation, which is these fringes are actually very close together. I know it doesn't look like that on the diagram. The angles are going to be very small, less than 10 degrees. So we can use a couple of assumptions. Now, with the first triangle I've drawn on the screen, I've got distance S is my left-hand side. Now, the next length of the triangle we can also say is S, even though it won't be exactly the same because the angle is small. It means that we can kind of make that assumption. And we said it's one wavelength. It's going to be the path difference. So therefore, the opposite side is going to be one wavelength. Now, we're going to compare this to the larger triangle on the screen. Now, the larger triangle on the screen, which I'm drawing out now, this blue triangle, has the D, the distance between the slits to the screen, as one side. But because the angle, again, is small, we can say that the hypotenuse is also going to be D. And the opposite is going to be the width distance between the two fringes. Now, using this, what we can do is just derive a couple of quick relationships using trigonometry. Say sine theta of the first triangle is wavelength divided by S, the slit separation. The bigger triangle, sine theta equals W over D. Now, these are both sine theta, so we can equate them together. Lambda over S equals W over D, and rearrange it for W, the width of the fringes equals the wavelength, times by the distance from the slit to the screen, divided by the slit separation. So that's our equation for the double slit formula. So let's have a look next then at how we can use that equation to understand what happens when we have different types of light going into our double slit. So what about instead of monochromatic light, if we had a lot white light, which is made up of all the colors? So using this relationship, the idea is if wavelength is bigger, then if everything else is constant, then the width of the fringes has to be bigger. So red light has the wider fringes because it has a higher wavelength, and blue light has narrower fringes or closer together because it has a lower wavelength. So if we were to view this on a screen, we'd have white light kind of surrounded by blue because it hasn't diffracted that much, surrounded by red, and then you'd have white, and then you'd have blue and red again, and so on and so forth. Obviously, you'd have grey, green, and the other colours of the rainbow in between, but that principle will work with all of those colours. Also worth noting, if you were to make the distance to the screen bigger, the fringes get further apart, and if you were to increase the slit separation, the width of the fringes would decrease because those two things are inversely proportional. Now, what would happen if I replaced the double slit with a single slit? Well, we still get an interference pattern, which I know sounds weird. It seems like the wave would just kind of go straight on and you'd have a big blob of light in the middle. Well, you do, but you do have these smaller fringes either side of it. So the intensity of the wave would look a little bit like this. So in the center, you'd have a really big peak, big maximum, and then you'd have these kind of smaller, dark and bright patches either side of it. So this central maximum, which is what it's known as, is very wide. It's 2 times the width of the other fringes. And central maximum, if we have monochromatic light, would just be one color. And then you'd have even maximums and minimums, maxima and minima, decreasing in intensity. So they're not even at all in terms of their intensity, unlike for a double slit. Now, for this equation, which are not given to you in your equation sheet for AQA, but you will be expected to use if they do give it to you. So let's have a look finally at diffraction gratings. So diffraction gratings, if you shine light through them, you'll find a diffraction pattern, but it won't be these fringes. Okay, they are called orders. But they look kind of similar. They are more spread out and they have a high intensity. And the explanation for how they form is exactly the same as for our double slit equation. So you have these patches of constructive and destructive interference. I've put a picture down here that can help because I won't be able to draw this in at all. So there is an equation to use when we're using diffraction gratings. I'm going to derive it for you now. So zooming a bit closer to our setup, we've got our diffraction grating, which is formed of many slits. So effectively, we can kind of use the same kind of ideas as for our double slit, but we're going to define our terms slightly differently. A small case d in this case is the distance between the slits, or in this case, the gratings. So the center of one to the center of another. And on the screen, we've got these things which we said were called orders. Now, the bright spots are orders, and the central one is the 0th order. Then going up and down from that, you've got n equals 1, the first order, second order, third order, etc. Now, just like with the previous derivation, we're only focusing on that first fringe, that first order here initially. Now, when we're looking at the first order, that means that the path difference between one ray from one grating to the next has to be one wavelength. If it was the second order, it'd be 2 whole wavelengths. But they have to meet in phase, so it's one wavelength. So looking at this little triangle we're left with down here, the angle, again, we're going to use small angle approximation, because this angle will be very small. And we can say that d, the distance between the two of the gratings, is equal to also so the hypotenuse is equal to the other side of the triangle. And that means that the one wavelength on the other side is our opposite. So using sine theta, again, we can say sine theta equals the wavelength opposite divided by d for n equals 1. Now, if we're looking at, instead of the first order, we can look at the second order. Well, this time it would mean it would be 2 wavelengths path difference. And then third order will be 3 wavelengths path difference, etc., etc. So we can modify this a little bit and say, instead of sine theta equals wavelength over d, we can say equals n wavelength over d, where n is just number of orders, which is our integer. So this leaves us with our overall equation, which you get given, which is d times by sine theta equals n number of orders multiplied by the wavelength of the light. Now, one of the trickiest parts in exam questions is that sometimes they don't give you what d is, the grating spacing. They'll give you the number of lines per meter or per millimeter. So what you've got to do to work this out is to convert to meters first. So in this example, I've got 300 lines per millimeter. That means 300 times by 10 to the 3. So that's 300,000 lines per meter. And then I've got to do 1 divided by x. That gives me the spacing between each one. Sometimes questions ask you, how do you work out what is the maximum number of orders that are observed? So how you do this, you rearrange the equation for number of orders and then realize, well, actually the maximum this angle can be for diffraction is 90. If it was any bigger, it would be reflection. So sine 90 is 1. So that makes our equation a bit easier. It means number of orders equals d, the diffraction grating spacing divided by the wavelength. Now, you'll have an answer. You need to round it down because you can only have a whole number of orders. So, for example, if it's 5.7, then it's 5 orders maximum that are visible. So refraction, we should be fairly familiar with the basic concepts from GCSE. If you have light entering a different medium that it can travel through, something like glass or perspex, it will slow down. Now, if we label the wavefronts on a light beam, which has a finite thickness like this one, it helps explain why that happens and why it changes direction. So as the wavefronts hit the perspex block in this case, because it's got a higher density, the light is going to slow down. Now, the light on the left of our diagram here, so I'm going to label this one A, that is going to hit the block first. So this part of the light beam will slow down first. B will slow down second. What that means is it will then kind of turn the whole ray of light towards the glass block, or towards the kind of normal of the glass block when we label that later. In addition to that, when it's traveling through the glass block, the wavefronts are closer together, which indicates that the wavelength has decreased. So it's slowed down and the wavelength has decreased also. Now, when it leaves the glass block, it will travel exactly the same as it was before. Same angle, wavefronts spaced back out again, and it will carry on as if nothing had happened. It's just bent when it was inside the block. So when it's back in air, it's back to its original speed. Now, the diagram you're more familiar with using, and the one we're going to be using today, is by drawing, instead of wavefronts, by drawing a ray of light as it goes through the diagram. That allows us to draw on the normal, so that's a perpendicular line to the boundary where the light enters. And we can label these two angles here. I is angle of incidence, R is angle of refraction. Now, if you were to measure the sine of the angle of incidence and the sine of the angle of refraction for different angle of incidences, you'll notice the ratio between them is constant. Now, that constant is different for each material, and it's known as the refractive index of that material. So it's different for glass, it's different for perspex, it's different for water. Now, this relationship only applies for a ray of light traveling from air into a material, into a medium. So, for example, here we've got light going from air into perspex. Now, that refractive index for air, for light traveling through air or a vacuum, is 1. For air, it's actually 1.003, and we can assume it's 1. But for different materials, it will always be greater than 1. That's because light is slowing down. So the angle of incidence will always be bigger than the angle of refraction. The other way we can define the refractive index is by saying it's the speed of light in a vacuum divided by the speed of light in the substance. Again, we're always expecting this to be greater than 1 because the speed of light in a vacuum, 3 times 10 to the 8 meters per second. Nothing can be higher than that. So this ratio either has to be 1 or something higher than 1. So the symbols we use quite commonly are C divided by CS. CS would be the speed of light in the substance, whereas Sp is just the speed of light. Okay, now knowing this relationship, we should also note that the wavelength changes when light goes from one medium to another as well. So if the frequency is constant, which it is, the speed changing also causes the wavelength to change. So we can rewrite this, instead of saying the speed divided by the speed in a substance, we can say it's equal to the wavelength divided by the wavelength in a substance as well. Now, what about a light that travels from, instead of from air into glass, if it travels from water into glass or oil into perspex, or two materials where neither of them is air? So we have to be a bit more specific about how we're defining our terms here. So we're going to change the labels on these two angles, the angle of incidence and angle of refraction, to just θ1 and θ2. And the relationship between them is, if I was to divide those two values, the sine of the two angles, then it would give me the ratio between the refractive index of material 2, i.e. what it's going into, divided by the refractive index of material 1, what material it's just come from. So the interface at the top of this diagram, you've got it going from water into glass, so N1 into N2. So the ratio between those two is going to equal the ratio between the sine of the two angles. So rearranging this slightly differently, we have what's known as Snell's law, which is given to you on your equation sheet. It was actually discovered in the 900s by a gentleman called Ibn Sal, but it's known as Snell's law in most modern physics textbooks. Okay, so adding to this relationship, we could also include the ratio between the speeds that we talked about earlier. So N2 over N1 equals the ratio of the speeds C1 over C2. Don't forget, both those have to be greater than 1. So if you're asked in words what Snell's law is, well, using that expression we wrote down earlier, we can kind of write that in word form. We can say it's the ratio of the sines of the angle of incidence and the angle of refraction. And then we can say that's equal to the ratio of the refractive indexes. You wouldn't unlikely to get asked it in word form, but it's worth knowing just so you can understand what that equation actually means. If you've ever done this refraction experiment, you might remember that at certain angles, the ray of light doesn't come out the other end. Something a bit unusual happens. If you shine the ray of light in at certain angles, it will refract through the first boundary, but it will, instead of refracting out the second boundary, it will kind of come along and start to refract sort of along the edge of the block, and eventually it won't even go along the edge of the block at all. It'll start to kind of reflect back inwards. Now, this effect is known as total internal reflection, and it's related to our third topic we're going to look at today, which is critical angle. Now, it's a lot easier to understand if you draw out a semicircle for the light going in, just because it won't refract at the first interface. It'll only interact when it reaches the second interface or boundary. So this purple line going in if I was to do it at just the right angle, it comes out at an angle of 90 degrees, or kind of along the boundary between the glass and air in this case. Okay. Now, this is what's known as total internal reflection, and it only happens under certain conditions. Condition number one is that this occurs when the light is going from a higher refractive index to a lower refractive index. So in this case, it goes from N1 to N2, where N1 is higher than N2. So it wouldn't work going from air to glass, just from glass to air. Now, the second condition is when the angle of incidence is larger than what's known as the critical angle. This effect occurs. Not if it's smaller than, it's got to be equal to or larger than the critical angle. So what does this term critical angle mean? So Snell's law, as from our previous example, applies to all situations, but in this case, there's a very easy simplification we can make to make it a little bit easier. Now, the angle 2, which we can see on the screen here, is actually a right angle, which is 90 degrees. Now, sine 90, we should know equals 1. So therefore, we can kind of exclude it from our equation, because 1 times refractive index equals the refractive index. So therefore, sine of the critical angle is equal to the ratio of the refractive indexes, N1 over N2. And the angle itself equals inverse sine brackets N1 over N2. So to find out the critical angle, we just need to know the two refractive indexes, and we can find it there. So in this case, for light going from glass to air, because the refractive index of air is 1, N2 equals 1. So this equation becomes even simpler, and it becomes inverse sine 1 over the refractive index of N1, which is, in this case, the glass. Now, as we said earlier, N1 has to be bigger than N2. If you do ever get it mixed up, though, it will just come up as an error on your calculator. So it's quite one of those equations you can't really get the wrong way around, otherwise it won't work. That's because the inverse of sine, anything bigger than 1, is impossible. So it just will come up as an error message on your calculator. So let's have a look at a couple of examples. Let's have a look at glass first of all. So refractive index of glass is normally about 1.5. So inverse sine 1 over 1.5 gives an angle of 42 degrees. Let's have a look at diamond then, right from the start of the question. This is a higher refractive index of 2.4. So that gives a critical angle of 24 degrees. So the fact it's got a lower critical angle means that actually light is way more likely to totally internally reflect from a diamond. Let's say it goes an angle of 30 degrees in. If it was glass, it's going to refract straight through because it's not bigger than 42. If it was diamond, on the other hand, it is going to totally internally reflect. That's because it's bigger than the diamond's critical angle, which is 24 degrees. So that explains why diamonds are far more sparkly than other materials, because light is reflecting through them and off them way more often than it would be through a substance compared to a substance like glass. Okay, to finish off today's video, let's have a look at the most common application of all of this, which is in optical fibres, which are used in communication for fibre optic broadband. Gives really quick broadband, which has a lot of information able to be transferred very quickly. They are also used in hospitals in endoscopes, in medical examinations, where they can feed to like a live camera feed so the doctor can see inside your body nice and clearly. So optical fibres, they look something like this. So the center of it is called the core. The outside bit is called something called the cladding. Now, we need to know how light behaves in this optical fibre and also what the purpose of the cladding is. So light goes in. Now, if it goes in at an angle greater than the critical angle, it will totally internally reflect. So I'm going to try and draw this in here. Now, it will be a lot shallower than this because I've drawn a bendy fibre. Fibres are usually not that bendy, but they will travel down to this surface. And again, if this is bigger than the critical angle, it will reflect again, and then so on and so on and so forth, all the way down the fibre over miles and miles of cable until it gets to someone's home if you're talking about fibre optic broadband. So the same rules apply here for total internal reflection as they do before. It's got to travel from a higher refractive index to a lower refractive index. So the cladding will have a slightly lower refractive index than the core, meaning total internal reflection is more likely to happen. That happens all the way along this kind of glass core until it gets to its intended destination. So the use of these fibres in fibre optic broadband presents a couple of challenges. When you're transmitting a signal of any sort, basically you're transmitting a bunch of zeros and ones in binary. So this signal, taking a very simple version of that signal, would be, let's say here we've got 0, 1, 0, 1, 0. Now, over time and over a lot of distance, the original signal becomes what's called degraded. So it would look a little bit kind of curvy and fuzzy and a bit of noise in there, which is particularly useful, especially if you've got thousands of these binary signals being sent at any one time. So we need to look at a couple of ways of how we can improve this and reduce the signal degradation in the fibre. There's two ways this can happen. One of them is called modal dispersion, and the other is called material dispersion. So we look at both of these. They're both mentioned on A-level specs, so it's really worth looking at how they can be reduced. So material dispersion, first of all, is when you have light shining through the optical fibre. If it's white light, different colours that make up white light refract by different amounts. So let's say I've got blue and red here. Because the wavelength of blue and red is slightly different, so 400 nanometers versus about 700 nanometers, the two colours will refract by different amounts as they're travelling through the glass. Now, what that means is after a couple of reflections, that won't be a problem. But after hundreds and hundreds of reflections, that will mean that the two colours of light will not arrive at exactly the same time. The signal will be degraded, will be distorted by these different colours that come in at different times. So how you'd say this in words, and you could be asked a diagram as well, so I'd make sure you learn that diagram. So how do we say in words is that different colours or different wavelengths of light will refract by different amounts. So therefore, the speed will change by different amounts, meaning they will arrive at different times at the other end where the signal is being received, meaning the signal has been degraded. So the solution for this is kind of obvious. Instead of using white light, we use monochromatic light. Light that has all the same wavelength. So it could be red, it could even be infrared, but as long as it is coherent light, monochromatic light, then you won't have that issue. Let's have a look next at modal dispersion. This one's a little bit trickier to get your head around, and the solution is a little bit trickier as well. So let's say even if I use red light for this to happen, what you'll notice is because light has a finite width to it, like one beam isn't just one wavelength of light, you'll find that this effect kind of occurs even with the same color of light. So that means that different parts of light will take different paths as they go through the fibre. So because they'll reflect at slightly different angles, over hundreds and over thousands of reflections, they'll end up at slightly different points by the end. So what we'd say here, they're not traveling different speeds because it's all the same color. So different parts of light beam will undergo different amounts of total internal reflection. That will then mean they take different paths, or they travel longer paths than others. So the same thing will happen. They'll arrive at different times. But do note here, it's not because they travel at different speeds. It's just because they are taking different paths that cause them to travel further, therefore take a longer time. Now, solution for this one, there's no perfect solution, but the narrower the core, the better. The narrower the core means the less reflections the light will have to undertake. Therefore, it's going to have this effect is going to be reduced. So our cladding on the core allows total internal reflection to happen, also prevents information or the light traveling between fibres. Fibres are very narrow. You'll often have bundles of dozens or hundreds in one big bundle because it is the best way to transmit this information without losing any information or with minimal signal degradation. For an object to be in equilibrium, there needs to be zero resultant force. There also needs to be zero resultant moments. So that means the principle of moments must apply, which is that the sum of all clockwise moments equals the sum of all anti-clockwise moments. I'm using the sigma symbol here to indicate sum. So the most easy example to understand is if you've got a seesaw, I've got two objects on either side. If I knew the forces acting downwards from each object and I knew the distances between them, were I to multiply the force by the distance for object 1 and object 2, they should equal each other, meaning the moments are equal. This could happen with multiple objects, but just for the sake of sort of ease of an example here, I've gone with one. Now, the slightly more advanced version of this is if I've got an uneven rod or it's pivoted, not in the center. So in this case here in the diagram, I've got the pivot towards the left-hand side, and that's because I've got an extra resultant moment acting from the center of mass of the rod or of the ruler. Now I'm going to label the force produced by that F3, as that's the weight of the ruler acting from the center of mass. But it's essentially like any other force. If I knew the value of it, I knew how far it is from the pivot, I can just include it in my moment calculation. So in this example, I'm going to have 2 clockwise moments and 1 anti-clockwise moment, which have to be equal to each other, same as before. The other type of example you can get with moments is one where you've got 2 support forces. So in this example here, if I've got 2 supports propping up a bridge or a ruler or anything like that, basically, I treat it as if I've got 2 pivots. So I've got to choose to take moments about one of the pivot points. Now, it does matter which one you choose, but it all depends on the situation for which one you take as your pivot. Same as before, you've got to consider the center of mass acting from the center of the bar or of the bridge going downwards. And once you've chosen a pivot point, so in this case, I'm taking the one on the left as the pivot point, I can just do moments like before. So I've got F1 D1 plus F3 D3 equals the anti-clockwise moment, which is F2 D2 in this case. So it's just about trying to simplify it and treating it as a normal sort of moment situation. And now, last thing to sort of know about here is what a couple is. So a couple in physics is a pair of two equal and opposite forces which act not along the same line of action. So the clearest example is the one here. You've got F2 going sort of up and left. You've got F1 going down and right. And they're both going to work to rotate that system about its axis. So they're in opposite directions, but not on the same line of action, if that makes sense. How you work it out is you work out the moment equals the force times by the distance between the line of action of the forces. So it'd be F1 times by D in this instance. Okay, now as well as sort of looking at moments, you could be asked with equilibrium to look at forces in a bit more detail, forces at an angle. Thoroughly recommend watching my video on resolving using trigonometry, absolutely essential for A-level physics. But you could be asked to do them to scale or to look at force triangles to help explain a situation. So in this example here, I've got a slope, I've got the weight acting downwards. Now I need to be able to sort of prove, let's say without numbers here, that the forces are balanced. Okay, so here we've got the weight of the object going directly downwards. We've also got a reaction force acting perpendicularly away from the slope. And when we've got the friction force going up the slope. Now let's assume the object's in equilibrium. So it's either traveling at a constant velocity or more likely it's going to be stationary in this scenario. Well, that means if I was to draw all the force arrows tip to tail, they would form a closed triangle, which indicates the forces are in equilibrium. If there is a small gap between any of the sort of tips and the tails of the arrows, it shows there's a resultant force. So here I've got a little gap between the tip of F and the tail of W, meaning there's a resultant force, which means the object would actually be accelerating. So let's start off with those graphs then. So we've got a displacement time graph here. It could be a distance time graph for this purpose as well. If I wanted to work out the velocity from a curved line, the object is accelerating. That's what the curved line represents here because its gradient is changing. If at any point I wanted to work out its instantaneous velocity, I would need to draw a tangent because I can't take the gradient without drawing a tangent. And its instantaneous velocity would then equal the gradient of that tangent, being change in distance over change in time. If I want to work out the average, I could then take the average distance and time and divide them. But there's a big difference in instantaneous and average velocity. For a velocity time graph, for a straight line, we should know that equals the gradient for that equals acceleration, which is change in velocity divided by change in time. Now, for certain objects that might reach terminal velocity, like a skydiver or like our ball here, or anything that experiences air resistance or drag or frictional forces, what's going to happen is the velocity is eventually going to become constant when, in this example, the weight becomes equal to the drag or the thrust becomes equal to drag force, which increases over time. For a velocity time graph, the area under the graph is equal to the displacement. Now, that's easy if it's a triangle or a rectangle. If it's a curve, at A-level, you need to count squares. You get marks for counting squares. Don't try and integrate it, even though that's technically the better method. At A-level, just count the squares if it's curved and estimate using that way. So let's draw some of these motion graphs for some tricky situations. The first situation we're going to encounter is dropping a ball. When it drops, it's going downwards. So it's going to have negative velocity, which is a straight line. As soon as it hits the ground at A, the velocity instantaneously, almost instantaneously, changes direction to go upwards to B, and then the same thing happens again. It's going to fall with a decreasing velocity, change direction at the x-axis a few times when it's bouncing. Now, to work out the gradient of the graph, the reason it's straight is because the only thing that's accelerating the ball is gravity, which has a constant acceleration, 9.1. So the gradient at any point of those downward slopes when it's being dropped should be constant, meaning it's a straight line. Now, if I was to draw a distance and a displacement time graph for a similar situation, but this time the ball is projected upwards instead of being dropped, we can notice the difference between distance and displacement. So distance means basically how many meters does the ball cover. So in this case, it goes upwards and then it sort of stops being a horizontal line and then it carries on covering distances because it's a scalar. We just draw it kind of carrying going upwards. Now, a displacement time graph will eventually come back down to zero. So it'll reach its peak and the displacement will then decrease back to zero, meaning the two graphs have a slightly different shape. Let's try and draw an acceleration time graph, which you won't have done at GCSE. Now, for our bouncing ball or our projected ball upwards, the acceleration is always constant, 9.81, as we mentioned earlier, so it's just a horizontal line. Next, we're going to look at Suvat equations or equations of motion. Where do they come from and how do we use them? So we're going to derive each of them from this initial equation, which is the definition for acceleration, change of velocity divided by time,
v minus u over time. Now, if we rearrange that to make v the final velocity of the subject, we should find that v equals u, the initial velocity, plus at. Now, if I was to graph this on a velocity time graph, similar to the ones we've just looked at, we would notice for an object that has an initial velocity and is accelerating, its initial velocity u is the y-intercept on that axis. And if I was to work out the area of this graph, the area under a velocity time graph is equal to displacement. So in this example, I've got a rectangle down here, which is area is ut, and this triangle up here, the area of a triangle is half base times height. So it's half v minus u, the difference between them, times by t. Now let's make this look a little bit simpler because it looks a bit messy at the minute. So we're going to group like terms together and separate out the brackets. So ut plus half vt minus half ut. Grouping together ut terms, I've got ut minus half ut, and I've got half vt there. So I'm going to factorize back in, and I've got basically half uv times by t, or u plus v over 2 times by t. So that's our second equation of motion, or a second Suvat equation. To find our third equation of motion, or third Suvat equation, we're going to substitute in equation 1, v equals u plus at, into the equation we've just found, equation 2. So instead of v, we're going to write u plus at. So we've got u plus at in our brackets. And we're going to group together our u's, so 2u plus at, and then we can start to expand out the brackets a little bit. So we've now got 2ut over 2, the 2's cancel, plus at squared, because we've times the whole thing by t. So rewriting that a little bit differently, I've now got s equals ut plus half at squared, or at squared over 2. Now for the final one, it's a little bit trickier. We're actually going to multiply two equations together. We're going to multiply together, acceleration is v minus u over t, and distance equals u plus v over 2 times by t. So if I multiply those two together, I've got as, or acceleration times distance on the left, and on the right hand side, I've got these terms I'm multiplying together here. Now hopefully we can see that one of the t's will cancel straight away, which is quite nice, leaving us with v minus u times by u plus v over 2. So if I times those together, I can kind of combine the brackets together and expand out the brackets. So if I expand out the brackets, I've then got v squared minus u squared over 2. And to rearrange this to make v squared the subject, we're going to get v squared equals u squared plus 2as, which is our fourth and final equation of motion. Now, how do you use each of those? Well, the first one you might notice has no displacement in it. So if you had the velocity, two velocities and acceleration, you could find the time, for example. The second one has no acceleration, the third one has no final velocity, and the fourth one has no time. So you have to pick your equation carefully, depending on what information you're given. Now, there is a slightly unofficial last equation, which isn't on your data sheet for AQA Physics, for example. And it says that the distance equals vt minus half at squared. So it's kind of a similar version to equation 3, but just replacing u with v, and that makes the minus half at squared negative. Let's look at projectile motion next. So we're going to apply some of these equations of motions to projectiles. We're going to go back to our original question right at the start of the video, which was if I was to project a ball horizontally and drop an identical ball at the same time from exactly the same position, which would land first. Now, well done if you said correctly that they both land at exactly the same time. I'm going to explain why that is the case in a moment. So when we're drawing these, the projectile projected horizontally, we need to consider the components of its velocity. Now, its horizontal component, we can see here I'm drawing the same size arrow, whereas the vertical arrow, the vertical component of its velocity, is increasing. Now, the reason for that is because we can treat the two components separately. The horizontal velocity is constant. We're not including air resistance here because you've given it an initial velocity, which will always be the same. The vertical component of the velocity will be increasing because of gravity accelerating it downwards or towards the Earth. Now, the velocity, the vertical component is increasing in exactly the same way as the ball that I'm dropping directly downwards. It doesn't have any horizontal velocity, and the arrows get bigger and bigger each time. So actually, the factor that determines how quickly it reaches the ground is its vertical velocity, which for both balls is identical. And the big conclusion here is that no matter what its angle it's projected at, you can consider horizontal and vertical components of its velocity totally independent of each other. So what we can use for horizontal motion, because there's no acceleration, we're not including air resistance here. The only equation that applies there is distance equals speed or velocity times time. So the initial velocity is the same throughout. For vertical velocity, however, there is acceleration. So we need to use any one of these Suvat equations we've just been through, depending on the information you're given and what you're trying to figure out. If you're given a ball that's projected diagonally at a certain angle, what you're going to have to do is resolve the components
in the vertical and horizontal direction, the components of its velocity, before you can do anything with it, because we're not considering diagonal components at all. So if you resolve it into the vertical and horizontal components, it's either cos or sine. Draw a little triangle out if you're not sure, so you can get that question right and you don't get the wrong way around. So in this case, it's u, the initial velocity, times by cosine of that angle, and then sine of the angle in the vertical direction. Newton's first law states that an object will stay at rest or at constant speed when there is no resultant force applied. Newton's second law says that force is proportional to acceleration and also proportional to the object's mass, and mass is inversely proportional to the acceleration, combining into equation F equals ma. Newton's third law, probably the most famous one overall, states that every force produces an equal and opposite reaction force on the object. Now, these laws are all well and good, but how to apply them is the tricky bit. So we're going to look at some applications of Newton's second law first of all. So let's imagine I've got a car dragging along a trailer behind it. So a trailer that's unpowered, got camping gear in it, something like that. So as the car moves along, we're going to consider the forces acting on the car. So we've got the driving force we're going to call F. We've also got forces acting opposite. We're not going to consider air resistance or drag at this point, like we do with lots of mechanics things. But we have got force going backwards, which is the tension on the sort of tow bar coming from the trailer, because it's sort of dragging the car backwards. So to kind of put these into the format F equals ma, which is our overall expression for Newton's second law, we can say F minus T equals ma. F going forward, T going backwards, the overall car is going forwards. So therefore it's F minus T to resolve those two equals ma. Now, from the perspective of the trailer, there's no driving force. So the only force is the one that's pulling it forward. Now, this is still tension in the tow bar. From the point of view of the trailer, the tension is pointing towards the car as it's moving it along. There's no backwards forces because we're not considering air resistance, so therefore T equals ma with a small case m. Combining these two things together, we can come up with our expressions. If I've just factorized down and I add those two together, we might notice the two tension terms will cancel. So we are left with F equals capital Ma plus small case ma overall. Next situation we're going to look at, which can become a bit trickier, are situations involving gravity. So let's look at a rocket going upwards. We've got thrust pushing upwards, giving it some propulsion. We've got weight pulling it back down, and not considering air resistance again. Now the rocket is accelerating upwards in the upwards direction. So therefore, if we put this into the format of T F equals ma, we've got T minus mg equals ma, because T pointing upwards in the same direction it's accelerating. So rearranging that for T, if I wanted to find thrust, equals mg plus ma, or factorizing it, we got m brackets g plus a. Next, and my favorite example is applying all this stuff to lifts or elevators. So you could do this with tension in a rope on an elevator, but far more interestingly, I like to do it with looking at the reaction force. So imagine you're standing on a set of scales on a lift. And the question is, where do you feel heavier, or where would the scales actually read slightly heavier than other times? So let's look at the forces we've got. We've got weight going down, and we've got reaction force, or the normal force pushing back up. Now, when you have this thing called apparent weight, or when you feel heavy, that's because you have a slightly higher R, or reaction force, than you would do otherwise. So let's look at the situations first up then. We've got the elevator, this time moving upwards, and it's accelerating in the upwards direction. So let's have a look at what happens to those forces. So put them into the format F equals ma. I've got R pointing up minus mg equals ma. So rearranging this for R, I can find R equals mg plus ma. Next, I'm going to have decelerating upwards. So if I'm decelerating, that's the same thing as accelerating downwards. So this time I've now got mg minus R equals ma. So rearranging that for R, I plus it to the right and take away the ma to the left. I've got R equals mg minus ma. I'm hoping you guys can see, regardless of what the numbers are in this equation, that R, when it's accelerating upwards, will always be higher because I'm adding together the two terms mg plus ma, whereas when it's decelerating, I'm subtracting them. So therefore, you're going to have a higher apparent weight, and you can see videos of this online. You do have a higher reading on the scales when you are accelerating upwards as opposed to decelerating. Okay, next situation we're going to look at is the pulley, which if you do A-level maths, you've probably done a little bit about as well. So inside the pulley, we've got two weights, two masses. We've got capital M and little m, either side of a pulley connected by one cord. Now, because it's one cord, there's a tension acting on it. And as you might be able to tell, the bigger mass is going to sort of be accelerating downwards and the smaller mass accelerating upwards. The tension is going to be acting upwards on the left one and also upwards on the right one. So come up with expressions for these two masses. I've got m minus t equals ma, so mg minus t equals ma, and the right hand one we've got t minus mg equals ma. So just like we did previously, we can combine these two expressions together, getting rid of t, because if you add them, the t disappears, being capital Mg minus little mg equals capital Ma plus little ma. So factorizing these out, I've got mg minus little mg equals a, and then brackets the two masses added together if I wanted to find out what one of those terms are. So don't memorize all these different terms, just make sure you can follow the steps of how I'm doing this. You need to be able to do this with exam questions rather than just memorizing words or key letters. So let's have a look at another way of expressing that Newton's second law, because we know it isn't F equals ma. However, we can also express it in terms of momentum. So we might remember from GCSE, F equals ma, a equals a change in velocity over time. So therefore, force equals m delta v over delta t. Now, another way of saying m delta v, or change in mv, is change in momentum. So we can also say resultant force is equal to the rate of change of momentum, rate being divided by time or per second. So that's another way of expressing Newton's second law. If I rearrange this equation slightly, I can come up with this thing called impulse. So impulse is defined by force times by change in time, or alternative times by defined by change in momentum. Now we can draw, if we were to have an object hitting another object, we can draw a force time graph for that collision. And the force normally starts at 0, then increases, then decreases again for, let's say, a golf club hitting a golf ball, for example. Now from this graph, the area underneath it equals force times time, which also equals the change in momentum. So if I add some numbers here, I can work out the area under this graph, because the area of a triangle is half base times height, which in this case is going to give me 50 Newton seconds, or 50 kilogram meters per second, though both those values are the impulse. If I was also asked to find the velocity, let's say they give me the mass is 50 kilograms, I could do that as well, because I know what delta mv is 50. I just divide by 5 to find the velocity is 10. Let's take on some more collisions now. Then we've got a particle hitting a wall. It's going to exert a force. Now, as it goes in with speed u and comes back with speed u, because it's a velocity, then the speed it comes out with is negative, because it's the velocity, it's in the opposite direction. So therefore, the change of momentum is going to be mu minus mu, which gives us 2mu divided by change in time. So therefore, there's always going to be a change of momentum, so therefore always going to be a force when, for example, a particle hits a wall. So there are two types of collisions overall, and we've got elastic collisions and inelastic collisions. Elastic collisions are defined by momentum and kinetic energy being conserved, i.e. being the same before and after. Inelastic collisions, you've only got momentum being conserved, kinetic energy is not. Now, inelastic collisions are much more common in nature, so car crashes, a bat hitting a ball, that kind of thing, where energy is usually going to be transferred into heat or other forms. Elastic collisions, we can consider particles in a gas that collide to be elastic, and they're really only talking about sort of particle and subatomic levels. We consider things to be elastic. So conserving momentum, we've got momentum before equals momentum afterwards in a closed system, meaning when there's no forces being exerted on the system. And we'll look at more examples of that later on when we do the questions later on in the video. So Newton's third law, we can also use that to derive conservation of momentum. So Newton's third law says that force on object A equals the opposite direction force on object B. We indicate that with a minus sign. So if I've got change in momentum over change in time for A, change in momentum over change in time for B, but negative, then what I can do is rearrange this a little bit slightly. So change in momentum can also be expressed as mv minus mu for object A, and also for object B, mv minus mu divided by change in time. So the time taken is the same because they're both colliding with each other. So we can sort of rearrange this a little bit and say MEA, the mass of object A times by its initial velocity plus the mass of object B times by its initial velocity is equal to the same thing, but with the final velocities, which is essentially what conservation of momentum is, which is really, really useful.
So to start off, if I was to combine two springs together, which arrangement would have a greater extension? To understand how to answer that question, we need to recap Hooke's law quickly. So Hooke's law states that if I was to apply a force to an elastic object, the force applied to the elastic object would be directly proportional to its extension. Now this applies only up to a limit of proportionality. We'll look at later some materials that don't obey this after a certain point. So that's Hooke's law. If we're looking at it in symbol form, we say force is proportional to delta L, or change in L, and the constant of proportionality we call the spring constant, sometimes called the elastic constant, which has the units of newtons per meter, or nm to the -1. So if you were to plot a graph, you might remember this practical, you might have done it at A level as well. You have the change in length and force. If I was to measure the gradient of force divided by change in length, that gives me the spring constant. It should be a nice straight line going through the origin to show that the gradient is constant. Let's then let's have a look at these different arrangement of springs and see if we can figure out which one has a greater extension. Now, all the springs here have the same spring constant K, and both arrangements have the same force acting downwards. So if I was to work out the extension, I need to know about the force. Now, for our first arrangement next to each other, the force is split evenly between the two springs, meaning each one experiences F/2. So to work out the extension, the spring constant is the same for both, but the force is going to be lower, meaning there's a lower extension for that arrangement. Talk about them parallel, they both experience the same force because the force is acting downwards on both of them, and both the springs are actually going to extend as well, have a change in length. So that means then you're going to have a greater change in length than there was compared to the arrangement on the left. Now, the arrangement on the left is called the parallel arrangement because the springs are parallel to each other, and to work out the overall spring constant, you just need to simply add together the spring constant of the individual springs. Next, for the one in series, it's a little bit more complicated, and I'll show you how we can go about working out what the spring constant overall is going to be. So if I was to add together for our series arrangement, the individual changes in length, I'm going to have individual forces divided by spring constants. But if the force is the same throughout all of them, I can replace the F's with a 1, so 1 over each one. So that means then for my overall spring constant, I can do 1 over the spring constant equals 1 divided by spring constant 1 plus 1 divided by spring constant 2, etc., which is sometimes known as a reciprocal addition, and it comes up with electrical circuits as well. So the idea is if I've got the same value for spring constant, which is by far the more likely scenario you'll be asked about at A level, if I have 2 springs, I'm going to have half the spring constant, whereas for in parallel, I'm going to have double the spring constant. Okay, let's have a look at force extension graphs then. So for Hooke's law, they are directly proportional, and that leads us to an equation for the energy stored in a spring, which is the area under this graph, which is half force times extension. It's a half because it's a triangle, so half base times height. But that rule applies for any object which you're applying force to, which is elastic. So substituting in Hooke's law to that, we can come up with another expression. I can replace F with K times by delta L, and that gives me half times by K spring constant times by extension squared, which is the alternative way of calculating the energy stored in a spring. Now, force extension graphs look a little bit different for materials that don't follow Hooke's law, or don't have a constant elastic constant or spring constant. For example, a polythene bag like the one you go shopping with. If you were to attach some weights on the end of it, it doesn't extend in a linear fashion. You'll get a graph that looks a bit like this. I've got force on the bottom and extension on the y-axis this time. Initially, I'm going to have a lot of force to make a little bit of extension. Then all of a sudden, I have a lot of extension, even though I'm not adding much extra force. So spring would be directly proportional. Add up like a polythene bag will be this blue line, the shape of it here, and it could have, for example, a rubber band as well, which another object which doesn't obey Hooke's law has a non-constant spring constant or elastic constant. So for our polythene bag, I've got a low force initially, then a large extension, then at the end I've got a large extension, even though there is not much force being added overall, which kind of makes sense if you imagine, like, you know, at one point when you're carrying your strop in, you put a lot of extra stuff in, it doesn't stretch much, then you put a bit more in, suddenly it stretches a lot. Now, there's a difference in our force extension graphs if I'm loading or unloading a material. So a loading graph, like this one here for an elastic band, and if I unload the weights from it, there's usually a slight gap between the graphs. Now, if I'm talking about the loading graph, the energy that that's stored in the rubber band would be the area underneath it, and if I unload it, that is the energy released as I'm unloading the rubber band. So there is a difference between those two energies, and the gap between those two graphs is the energy that's dissipated to the surroundings as heat. If you stretch an elastic band and unstretch it lots of times, you'll notice it gets hot. So this energy is dissipated to surrounding air as thermal energy. So what about objects then that aren't elastic, like our polythene bag? Once you stretch it past a certain point, what does the graph look like? So once we stretch our, let's say, a polythene bag past a certain point, if you start unloading it, it's not necessarily going to go back to its original shape. So this indicates it's a non-elastic material. It's not elastic, meaning it's not going to go back to the origin or back to its original length or shape. And the name for that is plastic. That's a plastic material, which we'll come on to a little bit later. Okay, so as we mentioned with our Hooke's law definition, every material will have a limit of proportionality. It might not be a great deal of force needed to surpass that, but our spring, for example, would be somewhere towards the end of the straight line. The rubber band polythene, there is a straight line for a small amount, therefore meaning a base Hooke's law, and those two things are proportional. Next, let's move on to stress and strain. So the idea behind stress and strain are they essentially give us more information about the material, because not all materials are springs or are elastic, and actually they don't factor in things like the cross-sectional area or the length of the material. So let's define stress first of all. So stress, which is given by this small case sigma, is force divided by unit area, or tensile force divided by the cross-sectional area of the material. So the units, forces in newtons, areas in meters, so therefore it's newtons per meter, but could also be written as pascals, so PA, alternative unit, which is identical to newtons per meter squared. Strain, we're going to use the symbol epsilon for, is the change in length, or delta L, divided by the original length. So it's extension divided by original length, which, if you look at the units, we've got meters divided by meters, so therefore strain is just a ratio. So it can be given as percentage strain sometimes. It's usually just a number, which is the ratio extension divided by original length. So let's talk about Young modulus of a material then. So Young modulus is given by the stress divided by the strain. So therefore we are going to have F over A divided by delta L over L, which looks very messy. So let's rearrange it slightly. So I've got F stays on the top, A goes to the bottom, delta L stays on the bottom, and if you're dividing by something on the denominator, you can put it at the top. So we've got FL divided by A times by extension. You're not going to have that given to you in an AQA exam board, so make sure you know how to derive it. And Young modulus is got the same units as stress, which is newtons per meter squared or pascals. It's worth noting that cross-sectional area is normally a very small value because 1 meter squared is quite a big material. So often you'll find Young modulus and stress given in megapascals, gigapascals. They're usually quite a large unit. So let's have a look at Young modulus graph. So one of the key parts of this topic is a stress-strain graph, which you can work out the Young modulus from. So I'm going to put strain on my x-axis, and I'm going to put stress on my y-axis. And this graph is going to be for a ductile material or a wire. And let's see what it looks like. Now, there is a required practical for this particular graph as well, usually stretching a metal wire and seeing what the Young modulus is, which you stretch usually using a vernier scale, so you can measure very small extensions because it won't stretch by that much. So let's say we've got our wire stretching. There's going to be a significant part of the stretch is going to be have a constant gradient, or it's going to have a direct proportion between stress and strain. So therefore, when these two things are proportional, we can measure the Young modulus only when it's a straight line, because that shows it's got a constant Young modulus at that point. So an alternative way of doing it is for a force extension graph, which is essentially what you're doing. You're applying a force measuring the extension, and we can use the gradient of that to help us find Young modulus. So using the equation I derived a couple of minutes ago, Young's modulus equals force times length over extension times area. So if I kind of separate out the force divided by extension, and I rearrange for the Young modulus E, what I'm going to get is Young modulus equals the gradient of the line times by the length divided by the area, which, because area and length are constant, is a kind of easier way of doing it rather than plotting a stress-strain graph. So let's have a look then for our stress-strain graphs. Now, these can be quite tricky, and one thing to remember is they're not necessarily chronological. It's not a time on the x-axis, so these things can happen at different times. You can take weights on, add them on to kind of change the stress. So after we get past this point here, which is our limit of proportionality, so that's where we can measure stress and strain up to, we'll find our next point is called our elastic limit. So our elastic limit is where it exhibits elastic behavior, and after that would exhibit plastic behavior. Now, these 2 points can be the same. You'll find them different on most graphs, just to distinguish between them. After that point, we have what's called the yield region, or sometimes called the yield points. Okay, so at that point, it's defined by, even if I'm decreasing the stress, the strain is increasing. So I have high amount of strain for very little or no stress added. Now, the top of the graph, the maximum stress reached, is called the ultimate tensile stress, or UTS. And as the name suggests, that is the kind of highest possible stress a material can withstand. It doesn't have to be the same point as the fracture or the breaking point. Sometimes it is, but you can take weights off, so the stress is decreasing before it then fractures once it goes past a certain strain. So this region here can also be termed a plastic deformation region. So that's because its material is not going to return to its original shape. So once it's past the elastic point, that's the kind of plastic region as well. So quite a confusing graph. Make sure you know the key points, how to label it and the shape of it. Bear in mind, as I mentioned before, this is for a wire or a ductile material, not for all materials. Most materials are not as complex a shape as this. But obviously most metals can be drawn into wires, and so therefore it's quite a common thing we're going to talk about. So let's compare some other materials then. So we've got our wire from the graph above. So that's ductile, meaning it can be drawn into any shape. In particular, it can be drawn into a wire. So that's only for metals. We've got other materials. So we could talk about things that are quite like brittle and things that are quite a lot of strain. So we could talk about glass as an example of something that's quite brittle. So the idea there is it shows very little strain before fracture, before breaking, indicated by the mostly straight line, then a tiny bit of strain before it breaks. We could also talk about materials and their strength, or whether they're strong. So they would have a high gradient on these graphs, or a high amount of stress needed for a small amount of strain. So not necessarily a metal, could be metal, but the higher the gradient, the stronger the material is, just like with our force extension graphs. Okay, to finish off the topic of materials, we're going to talk about density, which comes up at GCSE, obviously, so you should be relatively familiar with this. So let's talk first about how you'd measure the density for different objects in 3D. So if you're talking about a object like a sphere or a cylinder, you wouldn't need to memorize it because it's on your equation sheet, but you need to be able to apply the equations for volume of these objects. So they could just give you the radius of the sphere and ask you to work out the density if you know the mass. A cube is the easiest. You'd find, obviously, that's the length multiplied by itself 3 times. So to measure the mass of an object, we're going to use a balance to find that out. The difficulty comes if I've got an irregular object, such as like a screw or any shape that's not one of the above really. How do I find the volume of it? So we have what's called a eureka can, or a displacement can, which has a spout with a measuring cylinder underneath it. So if I lower an object into it filled with water, it will displace a certain volume of water. Now the volume displaced will be equal to the volume of the object. This is after Archimedes kind of discovered this way back thousands of years ago, and was able to figure out, well, that I can use that to measure the density of different objects. So tricky density questions can come up if you've got alloys or things with 2 different materials in them, like this example where I've got copper and tin mixed together. So what I'd have to do to work out the overall density or the overall mass is to work out the volume separately, and then work out the masses separately, and then use that to work out the overall mass. So to work out the volume of the copper, I do the mass of the copper divided by density. And then essentially kind of add them together. So lots of exam questions on this. Make sure you practice. They can be quite tricky to interpret.
So first things first, let's get some definitions out of the way. Current is the rate of flow of electric charge, which is given by delta Q, change in charge divided by change in time. Now, if we wanted to find out the total charge, but we only knew the charge on one electron and we knew the number of electrons, then we'd multiply together the number of charges, usually electrons, by the charge on each. For an electron, the charge is 1.6 times 10 to the minus 19. Now, normally we are talking of order of kind of billions and trillions of electrons in just 1 amp. So in 1 amp, if you were to work out the number of electrons passing through a point in 1 second, what you'd need to do is to sort of rearrange this equation a little bit. So you'd have n equals the current times by the change in time divided by the charge on 1 electron. In 1 second, therefore, we're going to have 6.25 times 10 to the 18 electrons in just 1 amp. When we draw out circuit diagrams, we are considering electrons to be traveling in conventional current, which is to say they're going from positive to negative. That's the way way diodes and other components are set up in circuit diagrams. However, we should know that conventional current is wrong. It is an assumption made in the 1800s, and physicists have stuck it with it ever since. We should actually know that electrons obviously have a negative charge, so would be repelled away from the negative terminal of the battery, meaning they would go towards the anti-clockwise direction in this instance. So let's go on to some slightly trickier definitions. Potential difference is a harder one to remember, which is the work done per unit charge. So V equals W work done over charge in coulombs. If I wanted to look at the electromotive force, you might notice the definition looks very similar, but we use a slightly different symbol for electromotive force. When we're talking about EMF or electromotive force, though, we are talking about the work done per unit charge supplied or given to charges to go all the way around a circuit. Whereas potential difference in general is the potential work done per unit charge that's available to the circuit. So there's a big difference between those two. We'll cover internal resistance and things like that later, where these two values are going to be slightly different. Units for each, we've got volts for PD, we've got joules for work done, and we've got coulombs for charge again. Now, lots of electrical circuits are designed to give power to an appliance like a bulb or a TV, microwave, whatever. So electrical power is the rate of work done, just like it is in any context. But using the equation work done equals PD times charge, we can replace the work done with that expression and then rearrange slightly to come up with a new expression for power. And therefore, we've now got Q over T, which is the same thing as current, and electrical power is equal to current times by potential difference, where power is in watts. Now, if I'm to use a different equation, V equals IR, Ohm's law, in this expression, I can substitute out V for I times R, meaning I've got power equals current times by current times resistance, which gives us P equals I squared R, which is another expression for power. Now, this one is going to be really important because whenever you have questions that talk about rate of energy lost due to heating, it's always going to be power equals current squared times resistance. Now, that's because if electrons go through a wire, they experience current, that's always going to cause heat to be lost due to electrons colliding and bumping past ions in the wire. Let's talk next about resistance. So the definition for resistance is the ratio of PD across a component to the current flowing through it, otherwise known as R equals V PD over I current. Now, when we're talking about electrons moving through, so that's the full definition, resistance is effectively an opposition to the flow of current. So it won't get any marks at A level, but that's essentially what it is. That's really important to know, roughly speaking, what it is, so we can understand in different circuits. So it's a measure of the opposition to charge flow. Now, the idea is for V, potential difference is energy per unit charge. So effectively, if you have a higher resistance, it means you need more energy to get electrons through the wire. Where we talk about electrons going through a wire, we're talking about current. So therefore, V's on top of our expression, current's on the bottom. So it sort of helps make sense of what actually a high resistance means. So Ohm's law describes something at constant resistance. It says that potential difference is proportional to current when something is at a constant temperature. So when the component you're talking about is at a constant temperature. So we'll give an example of a fixed resistor, for example. If I was to draw a PD current graph, you'd find it's a straight line through the origin, showing they're directly proportional. I could work this out using a circuit like this, where I've got a variable resistor to vary the current and PD values. I've got a voltmeter and ammeter to measure the PD and the current at different points, and I flip the battery around to get negative readings. Now, for a bulb is not at a constant temperature. Bulbs will get hot, so therefore it is not directly proportional. It has this sort of curved shape where the current eventually stops increasing and sort of becomes constant after a while. Now, why does this happen? So this happens because if you start increasing the potential difference, so the energy you're giving to the electrons, it makes the temperature increase because it's got more energy. So the ions inside the wire are going to vibrate more. So inside the lattice, they're going to start vibrating, which is going to increase the resistance. It's going to make it harder for the electrons to get through because the ions are vibrating, meaning it's not as easy for them to go through. Now, when that happens, that means you've got a higher resistance, which means current stops increasing. So it helps explain this flat part of the wire. Note that current doesn't go down, it just stops increasing. The third component we need to know is the diode. So in our diode, which I've actually drawn the right way around there, is if we have a current in one direction, we don't have it in the other direction. That's because a diode is designed to have a very high resistance in one direction and zero in the other, or very limited resistance in the other direction, meaning there's a really high current. This would also apply for an LED. Let's talk about two more components. We're not going to talk about current and voltage anymore, but we're going to talk about two semiconductors, meaning they conduct under certain conditions. The first one we're going to talk about is a thermistor. So a thermistor, if you increase the temperature, the resistance decreases, a bit like this. Now, in a regular piece of wire, when you increase the temperature, the resistance increases. Thermistors are made out of usually a silicon compound, which means they are designed to just be on the verge of conducting if you give them a bit more heat energy to supply to them. So these are called negative temperature coefficient thermistors. It's the fancy name for them, meaning temperature goes up, resistance goes down. Now the same thing applies for a light dependent resistor, apart from you can replace the word temperature with light or light intensity. It's literally the same situation. Next, let's move on to our electrical circuits themselves and how can we work out different values for current and PD using something called Kirchhoff's laws. So Kirchhoff's laws, and we need to know what they are, but we also need to know how to apply them. So Kirchhoff's first law states that current entering a junction or entering a component is the same as the current leaving it. So if I'm talking about a circuit here currently you see flowing branched off into three sections, the addition of I1, I2 and I3 is equal to the current that flows in from the left hand side in this example. So no current overall is lost. Now, because no current is lost, we said current is rate of flow of charge. So sometimes this is known as the conservation of charge principle, meaning you can't lose charge, you can't lose electrons, they don't just disappear. It's got to be the same before as it is afterwards. Kirchhoff's second law is all to do with potential difference. It's a little bit trickier to word and sort of imagine as well. So there's a couple of ways of phrasing it. Here's the one that makes most sense to me and helps us understand exam questions on it. It says that the sum of all PDs across a closed loop or around a closed loop is equal to 0. Now this doesn't even make sense because let's say I have 9 volts supplied and I have 3 volts and 6 volts taken out. That adds to 18. However, what we're doing is considering 9 volts supplied, it would be the electromotive force in, and then the 6 and the 3 will be taken out. So in this case would be negative. So the sum of those values is going to be 0. Now this is sometimes known as the conservation of energy law because no energy is lost. Bear in mind work done, PD equals work done per unit charge. So let's see if we can apply these in series and parallel circuits and come up with our rules for how current and PD behave in these two situations. So in a series circuit, if we've got two components which have voltmeters across them, what we'd find out is that the total PD supplied is going to equal to the voltage across each of those two components, so V1 plus V2. In a series circuit, however, if I'm going to put an ammeter at different places in between the components before and after, we should note that the current is going to be the same. The current does not change, it does not get used up. The number of electrons flowing per second before has to be equal to after. It's just their energy that changes. So we'd say then I1 equals I2 equals I3. Now, in a parallel circuit, it's a bit different because parallel circuits have multiple branches with usually multiple components and multiple paths the electrons can take. So if I've got a PD applied to the battery or to the cell here, if I look at the voltage across the bulb and across the resistance, we should find it's the same across each. Now the reason for that is because as the electrons flow, they can either flow through the first branch or the second branch, but never both, and they then meet to come back to the battery at the end. So that means the energy supplied per unit charge or work done per unit charge is the same for each electron. So each electron has the same potential difference. So therefore you can sort of treat this as two series circuits in one really, if you sort of cover up one and then treat the other one separately because no electron goes through both parts of the circuit. If I'm going to describe the current though, the current is slightly different. So the current when it leaves the battery is at its maximum and it will split into two in this case because there's two branches. So if I've got the initial current I and I've got I1 and I2, we can say the current total equals I1 plus I2 because the current will split. Just like in Kirchhoff's first law, it doesn't get lost, but I equals I1 plus I2. It's also worth noting here that giving parallel branches, you're going to increase the current because you can increase the number of paths the electrons can take. Next, let's look at resistance. In a series circuit, it's straightforward. The electrons go through any amount of resistors you've got all in a row. So the total resistance, you just add the resistors linearly. In a parallel circuit, it's slightly different. We've got what's known as a reciprocal formula for how resistors are added. So let me explain where that comes from and why it's really important to understand like where the equation comes from as well. We're going to start off by considering the current flowing through each branch. The current is given by the potential difference divided by the resistance. resistance. So the total current is given by the total potential difference divided by the total resistance. And each little part of the branch is equal to V1 over R1 plus V2 over R2, and keep on going depending on how many branches you have. Now we know from the law of potential differences in a parallel circuit that PDs are the same. So effectively we can cancel through all these because they're the same, replace with a 1, and then come up with the expression 1 over R equals 1 over R1 plus 1 over R2. So the total resistance you can find by adding the reciprocals of each of the resistances in the circuit. Now, this is really important to understand. So the more resistance you add, you'll find that there's more paths for the charges to take. So therefore the current will increase, meaning that the more resistors you add in parallel, the total resistance will decrease because the current overall is going to be increasing. So final thing with series and parallel circuits, with cells in series it's easy, you add them together, but with cells in parallel you might be thinking, well, why would you bother doing that? I'll explain in a minute. So what's the rule for adding cells in parallel? If I've got two cells like that, it's a similar situation with a parallel circuit. If each of them is 2 volts, the total PD is 2. That's because the electrons either go through one cell or another. They cannot go through both. So each of the electrons is going to receive a work done per unit charge of 2 volts. That's the maximum it can get. It can't be more or less than that. Why would you bother with this? So sometimes it's for longevity of batteries. If one dies midway through something, you can't access it, there's another cell that's easy enough to just take over. It's still going to provide an output PD of 2 volts. Next, let's talk about resistivity, which is kind of like resistance, but like a new and improved version of what resistance is. So resistivity takes into account certain factors about the wire, whereas resistance doesn't. So the resistivity of a wire also involves things like area and the length of the wire. So if we asked what had happened to the resistance if I had an increase in length of the wire, the two things are directly proportional. So what that means is if I was to have a longer wire, effectively I'm going to have more ions in the way for the electrons to try and get through, as opposed to a shorter wire, I've got less of it. So therefore I'm going to have high resistance the longer the wire is. Now compare that to the area of the wire, cross-sectional area. If I was to shrink the area down, I can find that actually there's less room for the particles to go through. So therefore there's going to have a higher resistance. So it's inversely proportional. Resistance is inversely proportional to area. The way to think about it is if you were to sort of increase the area of the wire, it's effectively the same as having additional parallel branches, which as we just looked at, that increases the current, decreases the resistance. So the reverse is true. If I shrink the cross-sectional area, I've got less sort of branches for the electrons to take, so resistance goes up. Okay, let's combine these into an equation then. So resistivity, which we use the symbol ρ for, the same as for density, is given by RA over L, where R is resistance in ohms, A is the cross-sectional area in meters squared, and L is the length in meters. How do we define resistivity then? It's the resistance of a 1 meter length of wire with a cross-sectional area of 1 meters squared. We could also express that with a potential difference in current instead of resistance, and sometimes you might see marks given or mark schemes that say things like the current provided for a 1 meter length of wire with a cross-sectional area of 1 meter squared if the PD is 1 volt applied across it. It's worth noting here the units for resistivity are ohm meters. You can find that out by doing a dimensional analysis of that equation. And you can also note that usually wires are very small cross-sectional areas in meters squared. So usually speaking, you're going to have A is going to be a very small value, so therefore resistivity is going to be quite small as well, sort of 10 to the power -6, -7, sort of roughly those order of magnitudes we're talking about here. Okay, so there is a required practical to do this, which I'll cover in another video, how to measure the resistivity of a wire, but that's the basics of it for now. Last thing we're talking about conductors. Is something called a superconductor, which is as exciting as it says. And now a superconductor is a material that has 0 resistivity when it's below something called a critical temperature. So the idea is going to have 0 resistivity below a temperature. If you were to raise it above that temperature, it just behaves like a regular material, have some sort of resistivity that will change with its temperature. But once you drop it below a certain point, certain materials just drop to no resistance, which is really, really, really cool, because that means you can have no heat lost. It's going to be basically 100% efficient, which means you can pass current through without having to worry about wasting energy and wasting heat and things like that. The downside is you have to get it to that critical temperature, which normally for these materials is really low. So normally like minus 100, 120 degrees, something like that. So these are used all over the world. These are used in particle accelerators to make the magnets as cool as possible, to make them as high magnetic field strength as possible, and also things like MRI scanners that rely on using powerful magnets to work. Next up, we're going to talk about internal resistance and EMF. So if I was to make this circuit here, where I've got an ammeter, a variable resistor, a switch, and I connect the voltmeter across my cell, we can take readings on the voltmeter and the ammeter and figure something out. So if I take readings on the ammeter and I do them at a 0 current, so with the switch open, and then I do 0.1, 0.2, 0.3, I'll notice that potential difference changes across these readings. It doesn't change in a way you'd expect. They're not proportional in this case. The voltage actually goes down across the cell the more current you add. The graph you'd find looks a bit like this. Now, like I said before, we've covered that voltage is proportional to current, so why isn't it in this case? What is going on that means that actually the voltage is going down? So what's actually happening here is that the EMF, so the work done per unit charge supplied to the circuit, is actually greater than the potential difference available to the circuit. This is due to something called lost volts, or volts being lost in the cell itself, which is due to this thing called internal resistance. Now, without getting into the chemistry of it, inside a battery, inside a cell, there are chemicals, usually lithium, things like that, which contain charges. Now, the whole point of a battery is that they are able to supply a potential difference, meaning the charges are going to be able to move inside the cell itself. Now, anything that moves, any charges that move, will have some sort of resistance associated with it, because there'll be some sort of collisions and energy being lost. So that tiny amount of resistance we call internal resistance. It's resistance inside the cell itself. So sometimes you might see it redrawn as a little resistor next to the cell to indicate it's got internal resistance. How I'd calculate that resistance is by working out the PD divided by the current. So the negative of the gradient of this graph would give me the internal resistance. There's an equation that expresses this all out in numerical form, which is that EMF is equal to the PD, or sometimes called the terminal PD, available to the circuit, plus these lost volts, which is given by the current times by the internal resistance in the circuit. We can rearrange this a little bit and rearrange for V. I've now got V equals the EMF minus I little case r, which we could do one more time, which is if I was to express the PD as I times by capital R, the resistance in the circuit, I can factorize out I and say it's equal to I times by the addition of both resistances. So be familiar with all of these. Your data booklet will give you the last one I wrote down there. Make sure you're familiar with all of them though. This helps make sense of our graph, because as we talked about, if I put it into y equals mx plus c, the gradient equals minus r, and in this case the y-intercept of my graph is equal to the EMF, which kind of makes sense because that's what is going to start on with zero current. The last thing we're going to look at today is potential dividers. So potential divider circuits, how can you make calculations involving them, and how might they be used in different circuits in different appliances. So potential divider, the principle behind it is very straightforward. You've got two or more resistors in series, and you've got a voltmeter across one of them or more than one of them. How does the voltmeter behave if you change the value of resistances? So currently I've got 6 volts plus 6 volts makes 12, because the resistor values are equal. So if I was to increase one of the resistors to 300 ohms, I know that it looks like 200, the 3 is there, 300 ohms, I was now in a ratio of 3 to 1. So how do I split 12 volts into a ratio of 3 to 1, where it's then going to be 9 volts across one and 3 volts across another? Now, one way of thinking about this is that in series circuits, current is constant, so therefore PD is proportional to resistance. Another way of thinking about it is if I increase the resistance, I need to apply more energy, more work done to get the electrons through. So that way you can consider sort of voltage and resistance to be proportional. So in this case, the PD times the resistance across each component is going to be equal. So I can then say the ratio of V1 over V2 is equal to the ratio R1 over R2 in this case. So the ratio of PDs is equal to the ratio of the resistances. Now, one way of working this out is by using the potential divider equation, which is basically the same thing expressed in mathematical form. So V out, the potential difference out, equals the potential difference in, times by R1, the resistance you're measuring across, divided by the total resistance. Both methods work absolutely fine. Like in this case, I'm doing the same calculation to find that it's 9 volts. However, this equation is not in your data sheet if you do AQA physics, so therefore you are going to have to memorize it. So whichever one you want to choose, if you're happy doing ratios, that's equally fine and comes up on mark schemes all the time. So where are these things potential dividers used? Well, they're not really used when you've got fixed resistors, because that's not particularly useful, but they might be useful when we've got things like thermistors in one. So let's say, for example, I've got a thermistor and a variable resistor, and a question might say something like, what happens to the reading across V1, so across the variable resistor, if I was to increase the temperature? So first things first, if I increase the temperature, we learned earlier that the resistance across the thermistor decreases. Now, what that then does is means that the potential difference across the thermistor also decreases. As we said earlier, they're proportional. Because the total PD is going to be constant, so let's say hypothetically 12 volts, the total PD being constant means that if the PD decreases across the thermistor, then that means the PD across the variable resistor must then increase to sort of make up for that loss. So the way you'd say it is has a greater share or a greater proportion of the total potential difference, which is constant. So that's the method that comes up in mark schemes all the time. You cannot change the total constant PD, so it must have a greater share or greater proportion of it. And these types of circuits are used in thermostats. So if I have an increase in temperature, the reading on the voltmeter, effectively the digital display, also goes up. You could have the same answer with an LDR, light dependent resistor, as well, used in streetlights. Exactly the same, apart from instead of temperature, you're now increasing the light intensity instead of the temperature. But literally everything else is exactly the same in terms of the circuit descriptions I've just written down in red. One last type of variable resistor that could be used in a circuit is called a rheostat. Effectively, it's a big long resistor. You've probably used it in a school practical. You slide it along and the resistance changes. Now, there's nothing to be too scared of here. It's just called a rheostat. Just pretend it's resistors in series. So if the voltmeter is halfway across, then you'd have 6 volts and 6 volts. If a question said something like it's a quarter across or 3/4 across, then you'd split it into the same ratio as before. So 9 volts and 3 volts. So even though it's one resistor, just imagine it's split into 2 and you'll be absolutely fine. Right, there we go. Well done for sticking with it till the end. Please leave a like if you found it useful, and yeah, keep an eye out for future exam practice videos on this topic.
So uniform circular motion, we are talking about a constant speed. Now, the speed as an object goes round in a circle is obviously different to its velocity. Its velocity is changing direction, but to work out its speed, we do distance over time. Now, in this case, for one whole circle, the circumference 2 pi r is the total distance covered divided by t, capital T, the time for one whole rotation. So v here is linear velocity. Definitely make sure you know the difference between that and angular velocity. Linear velocity is in meters per second. So to work out angular velocity, instead of displacement or distance over time, we do angular displacement in radians divided by time. So in that case, we can look at the total of a circle. So the number of radians in a full circle is 2 pi. So for one full rotation, we do 2 pi divided by the time taken for one rotation, or the time period. Now, instead of this, we could then write, because frequency is 1 over time period, we could also write 2 pi f. Both of them are equally valid. And that makes our units for angular velocity radians per second, or rad s to the minus 1. So make sure you're clear with those key terms. Otherwise, when you get to them with certain questions on circular motion, you will come unstuck quite quickly. Now, please make sure you put your calculator in radians mode for any questions to do with this. These equations only work if you have got your calculator in radians mode. As a recap, 1 radian is the angle swept through when the arc of an object traveling in a circular motion is equal to its radius. So when s in this diagram is equal to r. Now, to convert between them, we need to do degrees to radians. We need to divide by 360 times by 2 pi, or just learn this conversion here, and you flip the fraction to convert from radians to degrees. So these equations here can sort of be linked together to find an expression for linear and angular velocity. So we see here linear velocity is 2 pi r over t. Angular is just 2 pi over t. That means we can say linear velocity is equal to angular velocity omega times by r. So if you ever want to convert from one to another, then you just multiply or divide by r, depending on which thing you're trying to convert from and to. Let's look next at centripetal acceleration. So if I've got an object going in a circle, let's say a car going round a roundabout or doing donuts in a car park somewhere, it's going to go in a circle. There's going to be an acceleration. That's because even though if it's going at a constant speed, the velocity is changing because the direction is changing. As velocity is a vector, acceleration is change in velocity divided by change in time. There must be an acceleration occurring. Now that acceleration is directed towards the center of the circle. meaning that it's constantly accelerating towards the center. And that's basically anything you see the word centripetal from, it always means sort of towards the center, or something going in a circle, something towards the center. To calculate the centripetal acceleration, the equation is acceleration equals velocity squared divided by r. Now, once we know an acceleration, we're basically just going to use F equals ma to find the expression for centripetal force. Now, if acceleration is towards the center, the same thing must apply about the force. There must be a force acting towards the center of the circle as well. There's loads of different examples of this. We've got my car sort of doing donuts, going around in circles. That's going to be kept in the circle. The force towards the center is going to be by friction. And we've got planets orbiting the sun kept in their orbits by gravity. And you've got a plane that's going around a circle. That's air resistance allows it to do that, pointing in the circle, and so forth. You can even have just people twirling something around their head. That would be tension that keeps them the object in a circle and stops it from flying off. So using F equals ma, I can just sub in our equation for acceleration, v squared over r, and come up with F equals mv squared over r, or m equals omega, the angular speed, squared times by r. That means that if I've got higher mass, I've got a higher force. If I've got higher radius, I've got a lower force. If I've got higher velocity, that means the force increases as well. Okay, so now onto those all-important applications. Can you apply these laws in different situations to calculate something? So our first situation doesn't appear to be circular motion initially, because I've got a car going over a hill or like a small bridge, something like that. However, if I could consider the forces on the car, we can use centripetal motion, centripetal force to work something out with it. The idea is that for this bridge or for this hill, because it's a curve, we can sort of consider it as a full circle with a radius, meaning that we can sort of consider the centripetal force on this car as acting towards the center, which here would be downwards. Now I've got weight going downwards, I've got reaction force going upwards. Both of those we have to express together to equal mv squared over r. Now here it's going to be mg minus r, because mg is already pointing towards the center, r is pointing the other way. Now, second situation we're going to have a look at is like a stunt motorbike or a roller coaster, something like that, that's going in a sort of loop-de-loop, so going up and around in a circle. So at the top of the loop, that motorbike, we've got mg going downwards again, but the reaction force the motorcyclist experiences from the top of the loop is also going down. So in that case, because both these forces are going down, we're going to have the expression mg plus r equals mv squared over little r, the radius of the circle. In our next example, we're going to look at a situation where you experience forces at the top and at the bottom of a circle. This would be like a big wheel or like a roller coaster type ride, where you're sort of flung around in like a loop-de-loop type scenario. So position A and B. So A is at the top, B is at the bottom. We don't worry too much about the sides because they're kind of equal to each other. Reaction force equal to mg in those cases. So at A, we've got the same situation as the motorbike, and we've got mg plus r equals mv squared over r. At the bottom, I've got r goes towards the center. The weight is pulling downwards. So this would mean r minus mg equals mv squared over r. Now, questions could ask you, or where might a person feel heaviest or experience the highest apparent weight? Now, in this case, what they're asking you to do is to figure out which place would have the highest r, or the reaction force. Now, for our example here, at the top, if I rearrange the expression for r, I'm going to have mv squared over r minus mg. And at the bottom, if I rearrange for r, I'm going to have mv squared over r plus mg. So no matter what those values are, the term at the bottom is always going to be bigger than the term at the top. So where the person feels lightest, the reaction force is always going to be lowest at the top of this ride. Now, going back to our car going over a hill, we'll give you an example of something else you can be asked to figure out from a situation like this. You could be asked to work out what might be the minimum speed before a car lifts off the ground or sort of leaves the bridge. So in this case, you've got to figure out, well, if it's leaving the bridge or leaving the surface of the road, that means r is equal to 0 at that point, at that instant. Now, this makes our equation a little bit easier to deal with. I've just got mg equals mv squared over r. Cancelling the m's, I can substitute, I can rearrange for v, and v equals big square root g 9.81 times by r, the radius of the hill if it was part of a bigger circle. So I can work that out, work out the minimum speed. I could do that with any situation. I could do it with a motorcyclist at the top of the ride, anything like that. The minimum speed is always an r equals 0. Now, one of the hardest examples and a derivation that you could be asked to do, it did come up in a paper one past paper, I think 3 or 4 years ago, is to look at like a banked track. Now, the situation here is a car, just like in NASCAR or something like that, is going around a circular track, but it's banked. It's not flat, horizontal. It's kind of lifts up a little bit. So in this example, for my diagram, the car's going round and round, but the car in my diagram is sort of coming out of the page, sort of towards you on that bank. So labeling the forces, we've got mg going downwards, and I've got R, the reaction force is not going up, it's going perpendicular to the slope. So because it's banked, it's at a slight angle. And the center of the race, or the center of the track, in this case, is towards the right. So we have to be mindful of what centripetal forces might be acting there. Now, some questions could ask you sort of to express in words, well, why is it maybe you need less grippy tires, or you don't need as much friction to keep the car in a circle? Well, in that case, that's because there's a horizontal component of R that is in the direction of the center of the circle. So that means R is at an angle, but there will be a component of it that goes horizontally to the right and a component that goes upwards. So therefore, we need less friction overall to be able to keep it going in a circle. So if I replace that overall expression for R, we could do it at the wheels. We could have R1 and R2, both pointing perpendicular to the slope in this case here. And I'm going to redraw those as slightly easier to understand triangles that aren't so messy, where theta is the same angle as the slope makes with the horizontal. So if I've got R1 there, I've got theta here, we can come up with expressions vertically and horizontally for R. So vertically, I've got the adjacent side, so that's going to be R1 cos theta, and horizontally, in this case, I've got R2 sine theta. So the R1 cos theta is acting in the opposite to the direction of the weight, and R1 sine theta is acting in the direction of the centripetal force. So we can basically do a couple of little neat equations here and come up with a simplified expression for speed and the speed needed for the car to travel at. So if I've got R1 plus R2 sine theta, that equals mv squared over R. So that's in resolving horizontally. If I've got R1 plus R2 cos theta, and that's vertically, that balances out the weight, or mg. Now, those two expressions can simplify down if we divide them a little bit. So I'm going to divide expression 1, so the one with sine it, divide by expression 2. And we got the R1 plus R2 is going to cancel. That should be obvious. Sine theta over cos theta, that's going to become tan theta. And the right-hand side, I'll write it all out, but hopefully we should be able to spot that the masses are going to cancel as well. So we're going to have tan theta equals v squared over r divided by g, so v squared over rg. So if I want to work out the angle, and if I knew the speed and the radius of orbit of the circle, I could sort of work that out easily, or work out the speed if I knew the angle and the radius of orbit of the circle. There are lots of other examples though, and let's say you've got a skateboard or an object in sort of a curved ramp going back and forth, side to side. That's simple harmonic motion. You've got suspension in cars when they go over a bump, the springs in that cause them to undergo simple harmonic motion. So what on earth is it, and how can we make calculations using it for A-level physics? So for any object or system undergoing simple harmonic motion, or SHM, there's a very, very key and very precise condition that needs to be followed. That condition is that its acceleration needs to be proportional to its displacement and in the opposite direction. Now, opposite direction, direction is really important here. They can either point away from the equilibrium or towards equilibrium. So that's what we mean when we say opposite direction. Now, I'm going to draw some graphs out now for an oscillating system, and we're going to prove to you that this is the case. So let's take our simple pendulum. So simple pendulum, very similar to a swing, just suspended from a point, swinging back and forward from the equilibrium line, sort of left and right. Now, if I'm going to plot out a couple of graphs, we're going to do displacement time graph, we're going to do velocity time graph, and acceleration time graph. See what those graphs look like and how can we sort of demonstrate the condition I've just laid out for you. So first of all, let's look at displacement. Now, displacement has to start from a maximum. Now, we're going to term the left here positive and the right negative. It doesn't massively matter as long as you're consistent with your direction for all three graphs. Now, in this case, for displacement, it's going to follow a curve like this. It's going to go down to zero displacement at the equilibrium point, then go negative, then positive, then negative, and so on and so forth, which has this sort of cosine type shape here. Now, if I'm really careful and I plot out the different parts of the curve, I can use this to plot a velocity time graph. Now, where the velocity is going to be maximum is actually in the middle at the equilibrium point. And where the velocity is zero is actually where the displacement is maximum. So let's draw this out then nice and carefully, see if we can plot our velocity time graph. So I said velocity starts at 0, and it's got to be at 0 every time the displacement is at a maximum for our pendulum. So it looks a bit like this. We've sort of got an inverse sine graph here, which would normally start from positive, but in this case, it starts off negative because it's going towards the negative direction. Let's plot our acceleration time graph. And now acceleration is 0 in the middle, 0 where the velocity is maximum because the acceleration is not changing, it's going constant speed very, very briefly. And it's going to be at maximum when we've got the pendulum slowing down and stopping at either end where the displacement is a maximum. So let's plot our acceleration time graph on then. It's going to be negative and maximum at the start because it's accelerating in the negative direction. It's going to be 0 where velocity is maximum. So we have a little shape like that, which, excuse my drawing, should be a little bit better than that, but imagine that's a perfect curve. Let's have a look at displacement and acceleration now. If we have a look at those two graphs, we can hopefully spot they are exact mirror image of each other. So when displacement is positive, acceleration is negative, and acceleration is negative, displacement is positive. So that shows us that they're proportional, but they're in the opposite direction. Expressing this in an equation, we can say acceleration is proportional to the negative of the displacement, and the constant of proportionality is equal to omega squared. Same omega from circular motion, it's 2 pi f, or 2 pi over t, where t is the time period and f is the number of oscillations per second. So this equation is in your equation sheet. I would always use it. Always use equations to help you with definitions where possible. Hopefully you can see that omega is a constant, and it's got a negative sign there, so that can lead you to a clue for the two conditions for simple harmonic motion. Now the phase difference between these graphs, and we need to talk about as well. So the phase difference between x and v, hopefully we can see that v lags behind x by about 3/4 of a cycle, or x is in front of v by 1/4 of a cycle, which is 3 pi over 2. V and a, if I look at the difference between those, that's going to be 1/4 of a cycle again, if you look at how much out they are, so it's pi over 2 radians. And x and a, that should say a there, that's going to be half a cycle out, as we discussed previously. One's positive, the other's negative, so that's pi radians. There is a general equation for the displacement at any point. Now, displacement, we said, is a cosine graph. So x at any point is equal to the amplitude, or the maximum displacement, times by cos of omega t, where omega, as we said earlier, is 2 pi f. So for a simple pendulum, the only factors that affect the time period are the length of the pendulum. That's an L. I know it looks like a V. It's sort of an L on its side. And acceleration due to gravity or gravitational field strength. So different planets will mean the pendulum takes different amounts of time to do one oscillation. But where does this equation come from? So we're going to derive this equation now using a little bit of neat physics and a couple of sort of trigonometric relations. So this equation only works for small angles. We're going to use the small angle approximation. When you do the practical for this, you have to make note of that as well. You cannot do too high an amplitude, or this equation won't hold. So if I consider my pendulum bob, I've got the weight going downwards, mg, and the direction I've labeled here on the diagram is theta. That's the same as the angle between the pendulum and the equilibrium point. So if I resolve the weight into its perpendicular components, I've got mg sine theta going in the direction the pendulum is moving, and mg cos theta in the direction of the pendulum itself. So a restoring force is acting on the pendulum to bring it back down to its original equilibrium position. Now, this restoring force is provided by the weight of the pendulum, which is here equal to mg sine theta. It's negative because it's going towards the negative direction. If I was to express the acceleration, I'd say that force mg sine theta divided by m, meaning I can cancel the two m's, which gives me minus g sine theta. And rearranging for sine theta, that equals a over the negative of g. That's our first expression for sine theta. Our next expression we can derive using our triangle up here in the diagram. Now, for small angles, we can consider the arc the pendulum moves through as a straight line, which is the displacement. It's not really, but we can approximate it. So using a bit of trigonometry, we can say sine theta equals x, the opposite side, divided by L, the length of my pendulum. So let's equate these two together. So I've got x over L equals a over minus g. Now, acceleration we said earlier is equal to minus omega squared times by x. Omega equals 2 pi over t. So if I square all that out, I'm going to get minus 4 pi squared over t squared times by x over minus g. Next, we just cancel out the x's, and this is starting to look a little bit like our expression from earlier. We're just going to use a bit of algebra to solve for t, basically. So I've got g over L equals 4 pi squared over t squared. put the t on the other side, which gives you 4 pi squared over, and now I've got L on the top and G on the bottom, and square root the whole thing, bringing the 4 pi squared out to be 2 pi, gives us our expression from earlier. The next derivation we're going to look at is, instead of a pendulum, we're going to look at an oscillating mass spring system. So by that, and it is in one of the required practicals as well, which is to look at, instead of a pendulum swinging back and forward, we're going to hook some masses onto a spring and see how much they sort of bounce up and down. The time period is related to the mass of the spring, the mass of the masses on the end, and the spring constant of the spring. So we can use that and measure the time period for it to bounce one full oscillation, and work out the time period. Now, the restoring force in this case is provided by the spring constant of the spring. Hooke's law, meaning that the extension is proportional to F, or F equals minus kx. So similar to before, let's solve that for acceleration equals F over m, so minus kx over m, and rearranging for minus k over m times by x. Now, from our general definition earlier, we said that acceleration equals minus omega squared times by x. So what that tells us is that actually we could rewrite k over m as omega squared. So omega squared equals k over m. So rewriting this, I can then say, so 2 pi over t, that's what omega is, squared equals k over m. And again, this is starting to look a bit like our expression. Rearrange for t squared, so 4 pi squared over m times by m over k, square root the whole thing, and we get this expression up the top here. Next thing I'm going to look at is energy changes in simple harmonic motion. So if I've got a simple pendulum, or it could be our spring here, but we're going to start off with a simple pendulum. We've got the amplitude, so in the negative direction, the positive direction. We should note that the gravitational potential energy varies like this, a sort of inverted parabola, and our kinetic energy varies like this. So kinetic energy is maximum when it's at equilibrium, and it's a minimum at either end. The total energy, I've done in a slightly different color here, remains constant, and that doesn't change, assuming there's no air resistance, there's no work done overcoming friction or anything like that in the system. To rewrite it for the spring, we'll just substitute out gravitational potential energy for elastic potential energy, because that's what's responsible for pushing this spring back up when it gets to the bottom of its oscillation. Now we're going to use the expression for elastic potential to derive our last expression for the velocity of an oscillating system. So potential energy, elastic potential energy, is half k spring constant times by x squared. That means the total energy available to the system is when x is at its maximum, so the amplitude being half ka squared. Now, total energy ET is equal to kinetic plus potential, so therefore kinetic equals energy, total energy minus potential energy. So I'm going to have those two expressions subtracted from each other, so half ka squared minus half kx squared. Now, hopefully we can notice I can simplify that down a little bit and say half ka squared minus x squared. Now, the next thing we're going to do is where it gets a little bit tricky. We're going to combine this with, so we've just said this is kinetic energy. So kinetic energy, the general equation is half mv squared, and we're going to equate that to our expression we've just found out, and then put m onto the right-hand side. So I've now got k over m. Now, if you remember back to earlier, k over m is exactly the same thing that's equal to omega, or angular velocity, squared. So I can now substitute in, instead of k over m on my right-hand side, I can substitute in omega squared. I can also get rid of some of the halves, because we don't need those anymore. So overall, we then can then derive v squared equals omega squared times by, and then to square root, spread the whole a squared minus x squared expression, and come up with our expression for the velocity at any point, which is on your data sheet, but that's where it comes from. Finish off the topic of simple harmonic motion, let's talk about damping and resonance. So damping, kind of as the name suggests, is a force that reduces the amplitude of oscillations in the system, basically makes the oscillations less. So there's some obvious examples, there's some less obvious examples, and there's different types of damping that we need to know about as well. So if I was to plot a displacement time graph, I'm going to plot the oscillations without any damping, let's say of our simple pendulum, or our person on the swing here over time. So the oscillations don't change, this will be undamped. Now, if I was to introduce some damping, let's say on the swing, imagine I was to suddenly switch a button and air resistance magically switches on. So what that would do is to decrease the amplitude, but gradually over time. So the amplitude of the swing, unless you're inputting any other force or energy, is just going to gradually get less and less and less. So this is an example of something called light damping. The oscillations of the amplitude of the oscillations decreases gradually over time. Next one, when there's no real analogy for this with the swing, is something called heavy damping.
So heavy damping would be kind of like if I was to just put the whole swings and the pendulum into just a massive room full of treacle, and gradually from the maximum amplitude it will go back to its starting position, but it will take quite a long time to do so, but there will be no oscillations. Last one is something called critical damping. Now, critical damping, it does have an analogy for the person on the swing. That's if the oscillations go to 0, and it happens in the shortest time possible. Now, usually this will be a quarter of a cycle. That's the minimum time it can happen for it to return to equilibrium. It doesn't have to be that often. It's a bit higher than that, which is quite hard to actually achieve critical damping. But in this example, that's just someone saying, like your mum or dad coming out and saying, no, no more fun, let's grab the swing, put it back to equilibrium position. It's taken a quarter of a cycle to return there. That will be an example of critical damping. And this is what car suspension aims for them to be no oscillations, for it to happen very quickly, although as I said, it is quite tricky to actually achieve that in real life. So resonance then. Resonance, we need to be really careful how we're defining not only resonance, but a couple of key terms to do with it. And we're going to stick with the pendulum as an example, or the swing as an example. So every system that oscillates will have a natural frequency. The natural frequency we define as the frequency a system oscillates at without any external periodic force acting. Now with the swing, if you get on the swing, you kick yourself off, you'll swing back and forward with a frequency. Let's say it's 1 hertz, 1 swing per second. That will be your natural frequency. Now there's something that's called forced oscillations or forced vibrations, and this would be when it's not oscillating as natural frequency. This would be when there's a periodic force applied to the system. Now that word periodic is really important here. Periodic just means as a constant time period, or constant frequency, is not varying. So the example of that would be if someone started pushing you but at a fixed frequency. Now, resonance occurs when both those things are equal to each other. So it's a resonance is when the frequency of the forced oscillations is equal to the natural frequency of the system. Now, quite often, if it was a longer exam answer, you'd then say the forced oscillations would be a periodic force, but I've defined that already, so I'm not going to say that again. So an example would be if the natural frequency of the swing is 1 hertz, if someone pushes you at a frequency of 1 hertz, they're going to push you right at the peak of your swing each time. You're going to increase in amplitude. So what happens when resonance happens is the amplitude increases to its maximum, the maximum it can be. If we were to do an experiment where we'd change the frequency of the forced oscillations of a system, we'd find that the amplitude would peak at the resonance point. Now this would be, for the first line, this would be happening with no damping. However, if I introduce a bit of light damping, what we'd find is that the resonant peak, or the peak at which the amplitude is maximum, shifts slightly to the left. It lowers that resonant frequency each time. So greater damping means you're going to have a lower resonant frequency, or lower frequency at which resonance occurs each time. You can also note that the peaks become a bit less sharp as well as they occur over a broader range of values. The last little thing just to squeeze in here is to talk about the phase difference. So the phase difference between x, the displacement, and the periodic force basically increases from 0, and when it gets to its resonant frequency, the phase difference is at pi over 2 at its maximum amplitude. Then it starts to sort of increase again until it gets to pi phase difference after that point.